Let's see, there have been a few, there's been many iterations over this week. Of course, it's been a very different week. I'm still learning what works and doesn't work on here. I believe it was in this class that, no, it may have been my yesterday morning class, that one of the students who was using an iPad could not access the messages. Are any of you having that trouble? Okay, I'll tell you some of, say again, did someone say something?
I'm not having trouble.
No one, okay. Here's how things are evolving, and they still seem to be evolving. When I started off sending things to people, I thought announcements was the way to go because that's how we used to do it in the old Blackboard. So I was sending things through announcements, and then I can't remember how or why, but I ran across the messages, and that looked like it was the same as the announcements because everything on my end was pretty much doing the same, or it appeared to be. So I thought it was just a shortcut that I didn't have to go through all the steps to do announcements. So I started using the messaging, and then someone told me, well, they basically said, I'm not getting any announcements anymore. I said, well, I was doing the messages. I thought they went as announcements, and I found out, no, they didn't. So that was my bad on my part. So then let's see, what was the order of things? I decided to start doing both messages and announcements, until I guess it was yesterday morning's class. I found out someone couldn't get any messages at all, the one with the iPad. So I thought, well, let me just do strictly with announcements. So I started doing that until last night when I tried to send your lab. I found out I can't figure out any way to put an attachment on an announcement. So therefore, I have to go back to using both. But I'll make everything that I can an announcement, like the things like the codes and the invite to Zoom and everything else. I will send those as announcements, but then the things that have to have attachments, I have to use the messages for that. Now for that one guy, and if I find out there's any others that can't open the messages, I'll have to find out who you are and send you separate emails. Okay, so that's the only way I can figure out to get things to everybody. But so far, everybody's been able to get the announcements and messages. Is that right? Okay.
Well, I got the announcer for this class.
Okay, good. And it was pretty late last night before I got to them. And I'll just tell you what my whole week's been like. On Monday, of course, I had my 3 classes, but I also had at least one meeting before the class, and I think I had either 2 or 3, one or two meetings after my 3 classes. So anytime that I wasn't in class, I felt like I was in a meeting. I had a few times I could check some stuff. Tuesday, I had 4 classes, okay? And I think I told you I had a meeting right after yours, and I think I had either at least 1 and probably 2 meetings on Tuesday. Wednesday, I had 1 before class, and I think 2 after class, okay? And then, well, that was yesterday. And then I had another one. Well, it's just they've been meeting me to death, okay? Everybody's trying to figure out how to get this stuff to work, and they want all of us in meetings to talk about it and to talk about changes. So I'm hoping those are almost over. I have 1 meeting tomorrow afternoon at 12:30. But I think that's all for this week. But I think they're going to have faculty meetings every Monday evening. And I think I'll have departmental meetings every Friday afternoon. And hopefully they'll cut out some of the other meetings. Okay. I see 13 participants now. I got one more who's come in recently. Who's the last one to come in? Who's this?
Jeffrey.
Jeffrey Jones, right? All right. Good. All right. So any other questions about, now some of you weren't here last time. I sure hope everybody knows we're finishing the term, and by the way, they're calling this kind of classes, where we meet regular time, interact with each other just like we would in class. They're calling these, let me think of the name first, not online meetings, but virtual. This is a virtual class. We meet at the same times, we meet at the same days, we do everything just as scheduled. The online classes, when you see those, and somebody else has come on, who's the most recent one? Number 14. Anyone see a name pop up? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I think there's one more who's just come. Maybe
you're the 14th person.
I am the 14th? Okay. All right. Good deal. So maybe I was the 13th before and Jeff had just come on board and he was the 14th. I don't know. All right. So anyway, these classes are called virtual classes because we're meeting just as normal, only in a virtual environment. Online classes are those for people who don't have regular times that they can meet, and people just put assignments out there and they have to complete the assignments in a certain time, and then new assignments are put out. That's a truly online class. So when you see that on the summer schedule, I know you guys probably aren't going to see too many of that because I think most of you are graduating, aren't you? Automotive students? Well, I assume you are. Yeah, most of you are graduating. So you won't have to mess with this summer. But for the rest of you, if you were going to come this summer, it's just going to be just like this. You will be in virtual classes unless you happen to sign up for an online class, and we'll be meeting regular times. Okay? Now, the next issue is the whole school, and this is why we've had to have so many meetings, are trying to get virtual as well. Okay? In other words, the business office now has a separate email address, businessoffice@lawsonstate.edu. Now that's business office written as one word, no spaces, no anything in between, just business office is one word at lawsonstate.edu. Send it to that. Someone will be in touch with you fairly soon. The records office, records, they don't say office, just records with an S at lawsonstate.edu. I think financial aid has probably got one. I don't know their specific address, but whatever you look. Now, earlier, I put this, I think, under messages. I sent you something from the dean that had a whole bunch of these officers with emails and with phone numbers. So go and check that out. I think it's under messages. And if you need to get in touch with someone, that was a partial list of about a week ago. I know some new ones have been put in since then. I haven't seen that list yet, but I know, like the business office, that wasn't listed before. Another thing is advising is going to be virtual. So if you do need advising, just go to I can't tell you where to go because it's brand new, but look on the system. You know how to search for things. Look on the system and find the advising module. I can't think what it's called, but I think it's called virtual advising or something like that. And there you can sign up for a day and a time, anytime Monday through Friday, 8 in the morning through 7 in the evening, Monday through Friday, and you can log in and request a 30-minute advising session, and someone will be available in every 30-minute segment out there. Okay? And now, if someone else already has that, you won't be able to sign up because there's, I think, just one slot each, but there's plenty of opportunities for you to get it. I'm having trouble with my power cord. If any of you see I'm being distracted here, I don't have a power light anymore. It doesn't mean I've not got power, but I found out when the computer gets hot, this light goes off. And like I say, I don't know if it's the light or it's just not getting power. I think it is because the battery's so weak, I think it would be showing up. But I can't get it to go. If you start losing me, let me know. I can't tell if this is going bad or not. Okay. Now, registering, I think you're probably going to have to do online registration yourself. You can get advice from the advising, but I don't know if in the advising module I would be able to put your schedule in. Maybe I could. I don't know. I haven't gotten on it to see, but I do know they have it out there. So use it for advising mostly. If you need help putting the schedule in, someone will help walk you through that too. Okay. Now we're up to 16, so we must have had someone new enter.
It's Brianna, Dr. Fowler.
Oh, excellent. Welcome back.
Thank you.
Anybody else? I know there's at least one more that recently added.
Jacob Dove, maybe?
Yes, that would be Jacob Dove, wouldn't it? All right. All right. Any more questions? So basically, everything at the college is trying to move to virtual status, okay? Anything that you could have had before. Oh, let me mention this one. Tutoring. The Space Center is the same way as advising. You can log on and request a time. Someone will be assigned to tutor you at whatever time you request. I don't know exactly how that one's going to work. I wasn't in the meeting for that one. But just about everything we had before when we were on campus, we have now. So take advantage of them. Any questions? All right. So let's move on to the physical science, if there's no more question. I forgot to make a mark, but I'm pretty sure we finished through 3.2, and we were getting ready to start 3.3, which is on page 70. Chapter 3 is energy, and 3.3 is energy flow. Is that different from anyone's memory? Did you remember us being somewhere else? I thought we did examples 3.7 and 3.8. 3.8 was the football player crushing a quarterback, and we talked about that one. I believe that's where we ended last time. What you think? Okay, I'll assume that's it. So we're picking up now with energy flow. Now you might ask yourself, why in the world do they use a verb like flow? Or that could be a noun, I guess, too. Well, at one time, and this wasn't that long ago either, probably well after Newton, and I'm guessing even into the 18th or 19th century, no one really knew what energy was. They knew there was this concept out here, and people had the concept that energy was some, I think they used the term ethereal fluid that a material possessed. They thought of it this way. You take a piece of wood, you put it in the fire, it burns, giving off heat energy, and the piece of wood basically disappears, okay? Reduces to ash. So they thought the energy, the heat, was stored somehow in that wood. And when that was released, the wood disintegrated. Now, I know that sounds probably a little silly to us today, but that's how they thought of it. They thought of it as a fluid, an ethereal fluid that you couldn't see, you couldn't measure, you couldn't do, but it had to be there, okay? So they started using terms like energy flowing because they thought it was a fluid. So that's why we're still using this sort of archaic term. But what we mean by that, I'm going to see if I can move this. You probably can't see it, but I can. It's a box here that always has my picture, which is bad, and two names in it, which is good. But so it doesn't interfere with my screen. Energy can do work. Remember, energy and work, just different sides of the same coin, you might say. Energy is the ability to do work. Work is the application of energy to get something done. So, I mean, that's what you do with energy. So, you can have energy doing work as work against inertia. And they give a pretty decent illustration here, somewhere. There you have it. I bet you most of you have had to push off a car before, haven't you? Some point or another. And hopefully it was a Volkswagen or something small like that, but it could have been bigger. That's, you were doing work against inertia. The car was at rest. It wanted to stay at rest. You had to be the unbalanced force to get it not to rest anymore. And it didn't have to be as big as a car. It could have been a wheelbarrow. It could have been anything like that. That's work against inertia. Yes. Oh. A little. I can hear someone saying something, but I can't make it out. Okay, one more time. Oh, I see. Okay, got it. Okay. Okay. You have to, I talk so loud, sometimes I'll miss somebody saying something. Okay, another is work against gravity. Of course, work against gravity is anytime you lift anything, because gravity's trying to pull it downward, you're trying to lift it up. You're doing work against gravity. Okay? Force times a distance. Okay? Did that have this here? Yeah. In the car, the force you put on it and how much you move the car. If you don't move the car, you haven't done any work against inertia. Inertia won. I mean, it stayed in place. But if you did get it to move, then the force that you exerted times the displacement, that was the work you did. Same thing with lifting a box. The force or the weight of that box is what's pulling downward. So you're lifting up with at least that equal force, and you lift at a certain distance. That's how much work you did. Work against friction. Okay? The gal here pushing a crate or something across a surface that probably isn't ice, so it's not really slick, and she's having to exert a force to push it. However far she pushes it, that's the work she does. If she pushes and grunts and everything else and can't get it to move, she's doing no work. No matter how much sweat she's doing or anything else, if it doesn't move, it's not doing work. Okay? That's force against friction. Now the next one is a force against shape. Now, I want to tell you a little dumb story on this one. When I was in grad school in Nebraska, a group of us decided to have a co-ed volleyball team. And I'm not very good at it, but I enjoy playing volleyball. So we had this team in a league, and we played them, sometimes, usually on the weekend afternoons or something like that. And I remember this, and we had this one really tall gal who had played in high school, and she was quite good, and a friend of hers had also played, I think maybe on the same team, and that little gal was just one of the best setters I've seen. And so the two of them were sort of the core of our team. The rest of us were just there to support, because they were really good. And we did all we could to get the ball to one of them so they could put it into play and hopefully score some points. Well, one afternoon, weekend afternoon, we went into the gym. We were sort of hitting the ball around, and we figured out the team we were playing then. They had this really tall gal, and she had her a really good setter, and we said, oops, we're in trouble, because they looked like pros, okay? Ours were good. They were really, really good. And sure enough, as the game went on, that setter could just set it up perfectly, and that spiker, I mean, she could come down, it would be flying straight toward the floor, at an angle toward the floor. Hard to deal with. So, if you know about volleyball, when you're playing it properly, each team is rotating but in opposite directions, You know, every time someone serves, you know, serve changes, the people on the offensive team move a little bit, move one position. Well, that happened here, and of course everyone was going to wind up against that gal at some point in the rotation. And when it was my turn to come, I was ready. I felt like I was anyway. And we had either served to them or hit it back to them. They got it up, got it to their setter, and their setter, I mean, put a perfect set under the thing. And this gal was rearing back, I could see, and getting ready to jump. So I went up with my hands as high as I could go, went up into the air to make as big of a obstacle there, hoping to get the ball, knock it back over the net. And that ball came down square into my face. I mean, perfectly into my face. Now, I don't know if you've ever played volleyball. That ball is not particularly soft. Now, it's not as hard as a softball or a baseball or a golf ball or even a football, but it's still awfully close to that of a football or basketball. It's pumped up pretty tight. And that thing hit my face, and I felt it touch both ears at the same time. I did work against the shape of that volleyball, okay? Big time. And it did work against the shape of my face as well. And that, unfortunately, it landed on my side of the net. It didn't at least have the grace to bounce off my face and go across the net. It went into the net and then hit the floor on our side. So we lost the point anyway. But I knew, all I could see was Wilson, you know, before my eyes went black. Okay. So anyway, that's work against shape. Theirs is a little different. They're talking about the spring, the shape of a spring. You can press against the spring and compress it. How much you compress it, the force of which you apply, times the distance that you compress it, that's the work you did on the spring. But with springs, you could also stretch the spring. So then the force would be in the opposite direction, but the displacement would be in the opposite direction too, and that would be the work that you would do. Force times the displacement in the direction of the force, or the force in the direction of the displacement. And then you can have work against combinations of all of the above: gravity, inertia, friction, shape, whatever. And in fact, most of the time, things are a mix of things. Okay? The next subtopic here is called energy forms. The work in energy just described those things we were just doing, so that was covered in the previous slide. Energy forms on the right-hand column of page 71 if you are following in the book. And here is an important definition for you right off the top. A definition for mechanical energy. Mechanical energy is defined to be kinetic energy plus potential energy. And let me tell you why that's really important today. You're going to be using that in today's lab. Now, the lab actually calls it total energy. We're going to call it mechanical energy. Okay? And I've looked for it. It used to be in the book that way too, and I can't find that specific phraseology. It is the sum of kinetic plus potential. It used to be stated that way, and I can't see it in the book quite that directly. But I wanted you to know that is what we mean by mechanical energy, the sum of kinetic plus potential. Okay? It talks about them both, but they never say this is what it is. It's the sum of the two. I'm wanting you to note that here. Okay? Another form of energy would be electrical energy. Now, these are not quite in the same order they are in the book. In the book, they talk about chemical energy next. But let me go back to mechanical. What was kinetic energy, by the way? Anyone remember the definition? Kinetic energy. The energy of motion, moving, exactly. Okay? And what was potential energy? The energy of Oh, Kirk's here. Say that again. Of position. Excellent. The energy of position. Fantastic. Yeah.
Here too, Jason.
Who is this?
You got me a while ago. Jason.
Okay, I couldn't quite make it out. It's a little...
Jason.
Jason Little?
Yeah.
Okay, great. Okay. Excellent. Anyone else come in recently that you haven't heard me acknowledge you? Okay. So, mechanical energy, basically, is the energy of anything mechanical. It's the energy of motion plus the energy of position. And like I said, today's lab, that's what we're going to be dealing with, mechanical energy. So and did everyone get today's lab? I know it was late last night before I sent it, but everybody got it? I hope you printed it off. If not, you can just jot down what answers we do, and we'll see. Because some people have had trouble getting into these lab simulations, but last time it seemed like everyone was able to get in. I believe it was Perrin who was having difficulties. Did you ever get into those other two? I guess he's not there. Okay. All right, so let's move on.
Lab simulations for a grade.
What's that again?
Are the lab simulations for a grade?
Yes, those are your labs, and the lab is 25% of your grade.
You said you make sure you can get into them. I haven't been able to get in the last two.
Say that again.
I haven't been able to get in them.
Okay, who is talking now?
Zane.
Zane. Okay. Well, you weren't here last time, but everybody seemed like they were able to get in it last time. Some of the people... Say again?
You're talking about this past Monday?
Tuesday.
Or Tuesday?
Yeah. Were you here Tuesday?
I tried to get in and it wouldn't. It said that we didn't have any. Like it wouldn't pop up. I couldn't find the thing to get on. Did y'all do anything Tuesday? Because I never got an email or anything. Yeah, we didn't get anything.
Okay. I send it to the whole class, and I don't know why some get it and some don't. Now, one thing early on I was doing was, and this may be before y'all came on today, I started off sending them as announcements. And then later I found people were sending me things through message. And on my end, they looked like they were the same thing. I mean, I clicked in different places, but how I sent an announcement and how I sent a message was almost the same way. So I thought it was just a shortcut to an announcement. And then I think in this class on Tuesday, someone told me, no, it was on another class on Tuesday, no, on Monday or Wednesday, someone told me, no, they're not the same thing. And then I found that out. So I started sending things both ways, trying to catch everybody. Then I found out some people can't get any message. It sounded like everyone...
I didn't get any because I've got every other notification except for Tuesday, so I figured we weren't doing anything.
Okay, Tuesday, I think I sent it both ways. I'm not sure. I started doing it both ways, and then this one I only sent by announcement.
In the announcements, it said your last announcement was like Thursday before spring break.
Okay, that's because I started sending it by the message, because I thought that was the same thing. I found out later it wasn't. That's why I went back to doing announcements. Do you know how to access your messages?
No, I didn't.
Okay. What kind of device are you using? Your phone or a computer or what?
Laptop.
Okay. Is it a Microsoft type computer or an Apple type computer? Microsoft. Okay. When you go to Blackboard in the class, the main room in the class, there's a gray bar that goes sort of near the top of the page. And that gray bar has a number of icons on it. Is this how y'all see it? Because all I see is the instructor side. I don't know what the student side looks like. But that gray bar has a number of icons. Now, Kurt, you send everything through messages, don't you?
Yes.
Okay. How do you get to your message?
I just go to the class, and then the top right corner of the page, there's an envelope icon that you click on.
Okay. Is it that thing that looks like an envelope?
Yes, sir.
Yeah, that's the one. That's what I see too. There's a gray bar up there, at least on our computer. It's a gray bar near the top of the page, not at the top, but near the top, and there's a bunch of icons on it. One of them looks like a sheet of paper with writing on it. That's the grade book. And another one looks like...
Messages.
What's that?
I can see the messages now, but there was no notification saying there was any there. Now that I click on it, it says there's 6 new messages, but there's nothing telling me that there was messages there before.
Okay. Now, after the day's over with, I take the message off. But I leave it up there until after we've been in class, because I didn't want 15 announcements of messages and someone goes to the wrong one. So it was there before class. And I'm sorry if you didn't know to look there, but yeah, I would say check messages. And for instance, last night when I was trying to send the lab, I found out I could not do an attachment to an announcement. So therefore, I have to send those through messages. So you may not have gotten your lab either. Do you see that in there?
I seen where you said something about it, but I never actually seen it.
Okay. Did everyone else get their labs? I thought some of you said yes.
Yes.
Okay.
Yes.
And how did you get it? Wasn't it through messages?
Messages.
Okay. And when you opened the message, was the attachment there?
Yes.
No?
Yes.
Yes. Okay. Was it Zane that was saying? Have you found it yet?
No, nobody in my class, like all the
What's that?
class, we were all asking each other.
Oh, I see.
We had class today because nobody had figured it out. And I looked on Blackboard, and there was nothing under announcements, and it wasn't showing I had any messages, so
Yeah.
we assumed we didn't have it.
Okay. Well, there were 9 people who were here, so some of them knew we had class. But from now on, I'm sending all the invites for the thing. I'm going to send those, go back to sending those through announcements. But you see, when I started getting things through messages, I thought this is how people are communicating. So that's why I started sending them through messages. Then I found out that not everyone was looking at messages, so I started sending them again through announcements. And for a while, I was sending both ways, but now I'm only doing announcements because some people can't get any. But if there's an attachment like the lab, that's how I've got to send it. I have to send it through a message because there is no way that I found to put an attachment on an announcement. So you're going to have to check both announcements and messages.
I didn't know that till now.
Yeah, well, unfortunately, I didn't know that they weren't the same for a while because from my doing them, they acted exactly the same. But then I found out later that no, they are different animals. Because you see, I don't receive announcements; I only send announcements. So I didn't know there was a difference there. So anyway, yeah, we have class every Tuesday, every Thursday at 1:15. Okay, every Tuesday, every Thursday at 1:15. If something does come up that is not going to happen, which I don't think it's going to happen, but if it does, I'll try to get everyone the word that it's not going to happen. Okay, but I'll try to send those things, the invites, through announcements, because it seems like more people get announcements than they get messages. But things like the attachments, tests, labs, those kind of things, I have to send through messages. I haven't figured out any other way to do it. So you need to check both. Okay? All right. Now, all the classes and all the labs are out there on YouTube videos. So all you have to do is go to the days that you may have missed and watch the YouTube video. The labs are there and the classes are there. Anything you missed should be there. I'm recording right now. If you see this little red circle in the corner with the clock near it, that indicates we're 35 minutes and 41 seconds into the day's class. And every class has been recorded and is out there on YouTube videos, and you can access those through Blackboard. Now, I won't say that they'll be accessible this afternoon. Today's won't. It's usually going to take a few hours for it to load to YouTube and then for me to get it transferred over to the playlist. But every one of them will. Usually by the end of the day it's happened. Today has been going awfully slowly. As I've looked at the other classes, only the early morning class was fully loaded. I don't know, maybe the second one's loaded now. I doubt if the third one is. So it takes a while for it to load to Blackboard. I mean to YouTube. All right. So you can pick up. The labs are all there too. I keep the recording on during the lab. I show you where to go. I show you how to do it and explain what you need to do. So do the labs and then turn them in. The first two that we did virtually, I just explained what you had to do. Take a screenshot of it and then also write up some stuff on it. That's all we did for the first two because that was my first time doing those. The last one, the one we did on Tuesday, I sent you by a message, and it's still out there, the lab assignment, okay? And that way you got to fill it out as you went. You don't have to write your own stuff. I found I was having trouble reading some people's stuff because the print was so light. This way it made it a little bit cleaner. And I sent the one for today's lab. And what we'll do in lab, some of you will be able to fill in most of the blanks. If you have it printed for you, you can fill in most of the blanks as we do them today. Other things you might have to do on your own. I won't do all the calculations for you today, but you can do the calculations, but you can get the basics down. So that's how you can do the labs. Just get them done, and get them to me. Now, how do you get them to me? If you have a way to scan them, you can scan them, or if you don't have a way to scan, take a picture with your smartphone, okay? Either way you get that file, then you can either email that to me. Several people have done it that way, and other people have sent it as an attachment to a message. Either way works. I check both emails and messages. Now let me tell you this, I'm way behind on grading right now, because I've had meeting after meeting after meeting this week, and all the time that I would have been grading, it seems like I've been spending in meetings. So hopefully after today, I don't think I have any other meetings today, but I do have to go over summer schedule, review that before they're going to release it. And then I also have a meeting tomorrow afternoon at 12:30. So after I finish reviewing the schedule, hopefully it's not in too bad a shape, I can get rid of that, and then I'll hopefully get some grading done today. But first I've got to print all this stuff, because everything that comes in I have to print before I can grade it. So it's a long process and I'm behind in it, but hopefully most of these meetings are over with. Not all of them, but most of them are, and I'll be able to spend more time grading. So get the things to me soon as you can. I'll get them done. Let me also say research papers. I've received 4 from this class that I've seen so far. Get those to me. If you have any past labs, for instance, lab 0, I think just about everyone's turned that in, except one person who hasn't been here at all. I think she may have been removed from the roll. I haven't seen that. because she has never shown up, and another guy has never shown up. Okay. Lab 1, which we did in class that last Thursday before we didn't come back. Only probably a third of you have turned that one in, and I know that I did send it to some of the people who weren't there on that Thursday. That one you're going to have to scan or take pictures and send me the pages. Now, some of you have been pretty clever and only send me the pages that you had answers written on. That's good. The less I have to print, the less I have to waste paper, the better. But be sure you send me all the ones you write on. Test 1, I still have several people haven't turned in test 1, and hopefully you've got those.
You told me you were going to email it to me, and I never got an email.
Okay, who is this now?
Jason.
Jason. Okay. Test 1. Now, you were there that day, though, weren't you?
The day in class?
No, the day that we took test 1. Did you just choose not to take it that day?
Didn't have enough time to take it after we got done with our lab.
Okay. Okay. Is there anyone else that still needs that? So, Jason, the only one?
I think there was only a handful of us that actually took it.
What's that?
I think there was only a handful of us that actually took it.
Yeah, but I sent it to a number of people. I don't remember how many, but evidently Jason.
And I did it too.
Who is this?
Parent.
Perrin. Okay. Okay, I'm going to put this under test 1. Okay. Chad, did you get yours? No answer from Chad. I haven't seen Capri since we started the online stuff, so I don't have one for her. Brianna, I sent you one, didn't I? Can't hear Brianna. Sam, did you get one? Sam not there? Say again?
I received mine, Dr. Fowler.
Okay, and that's Brianna, right?
Yes, sir.
Okay. Chad, did you get one?
Did I get what?
Test 1.
Yes.
You did. Okay. I haven't gotten it back though, have I?
No.
Okay. All right. Now, Miss Lewis, we haven't seen since we've gone online. Zach, we haven't seen since we went online. Eric, did you get your test 1? Eric, have we lost Eric? How about Sam? Okay. Well, I can't find out if you've gotten them if you're not on. So I know I'll send. Chad, you said you did have test 1, right?
Yes.
Okay. And you're going to send it to me, right?
Yes.
Okay. So Perrin needs one. Jason needs one. And so far, no one else who needs one has let me know that. But no, whoever said that, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 people have turned it in. So it was a pretty big handful that took it. Okay. Then Lab 2, a few people have turned that in already. Lab 3, just a couple have turned in Lab 3. Test 2, 1, 2, 3, 4, 5 have turned in Test 2. Now, if you've turned in recently, I just haven't gotten it graded yet. And
Where
then,
did you send test through?
what's that?
Where did you send test to? Like, was that in messages or is
Yeah, the only way I can send an attachment is through a message.
Okay, so
I cannot send it through an announcement. Okay, so look under messages. I delete the invites after we've had the class so it doesn't get confusing and people put in the wrong code, but I don't delete the tests and labs. They're still out there under messages. Isn't that where everybody's received them in messages? Yeah.
Yes.
Okay. So look under your messages. That's where they are. That's where they should be. If you're not getting the messages, I've heard that this version of Blackboard sometimes skips some people, and I don't know why. But let me know. And I will, like I said, send Perrin and Jason theirs. And have both of you checked in messages?
just now looking at it. This is the first time I've seen it. But I see chapter 2 and I see labs 4 and 5, so I'll get them done.
Okay, do you think you have it?
I see it.
Okay, so neither one of you need me to send it again. Okay. Okay. I thought I had sent those, but I wasn't sure. So Jason, you don't need it? Is that right? See, I can't tell who's talking. Jason doesn't need it and Perrin doesn't need it. Is that right? All right, good. All right. All right. Any other issues? I know it's all new for all of us, so hang with, but ask questions. You won't ever know until you ask. Okay? And the labs, hopefully you saw those too. And the labs that we did online. Now, one of the labs was done separate from class. That was lab 2, I believe it was, because I didn't have it ready in time for class, and I barely had it ready, but I did a YouTube video on it. Okay? Lab 3 we did in class. Okay? And lab 4 we did in class. And lab 5 today we'll be doing in class. Now, if you log off early, you're going to miss it, but it'll be on the YouTube video. Okay? Oh, and by the way, I forgot to do it last time. When it gets to be 3:45, you did tell me to stop, and we did do the lab, but I forgot to call roll again. So please let me know, remind me to call roll, because I need to do that as well, because I have to enter roll for both the class and the lab, and they get upset if we don't do our rolls. All right, any other questions?
Yes, could you send an email or something with all of like the due dates for everything? Because I mean that's kind of a
Okay. Who
gray area right now.
Who is this talking?
Jacob.
Forte. Okay. Okay. Blackboard assigns due dates. Okay.
Yeah.
I don't even notice it most of the time. Now that I realize they assign due dates and I see where they assign them, I try to change them. Now, some of the early things I didn't know. Ignore the due dates. Okay.
I knew they were wrong. They were just the days that you posted.
That's exactly what it does, and that's ridiculous. I don't know why anyone would program something to do something so stupid like that, but they did. So those that I've noticed, for instance, someone asked me about the research paper, and that's where I found out where they were. So I went in and changed all the research papers in every class to the last day of class. Does that mean I want you to wait till the last day of class to turn in your research paper? Absolutely not. As soon as you can get it done, get it to me. And usually on the labs and tests, if I see it and think to do it, I'll tell you, last night I didn't. Last night I was so tired by the time, I think it was after 10 o'clock before I got that one finished and sent. And I'll tell you today when we're doing it, I forgot to put something on there, so there's something else you'll need to write. But when we get there, we'll talk about that. But I know I didn't even think of checking the due date on that. Generally, the due date will be 1 week after we do it. Okay? Now, if you're not here the day we do it, plan for it to be 1 week after the day you do it, okay? Get it to me as soon as you get it finished. Don't worry about the due dates. There's no penalty or anything, but I'll tell you what I do not want to happen. I don't want everybody turning in everything on the last day of class. If that comes in that way, I'll tell you right now, I will not be a happy camper, and I'll not be in all that good a mood when I'm grading those things. And not that I'm going to do anything specific, but I mean just human nature. I'm not going to be feeling very good about it. So I might be a little pickier in the grading. So I would say get the stuff into me as soon as you can. Okay? Does that make sense? It's not being too harsh, is it? Okay. Yes.
It's Kaya.
Kaya, welcome. Okay, you just missed my spiel, huh? Or did you hear it?
No, I was on here. I heard it.
All right. So you figure you better show up. Okay, there you are. I see you now. All right. Anyone else joined the class recently? All right. We were on our, I guess, second or third slide. It's energy forms, and we were talking about these. We had talked about mechanical energy, and believe me, we'll be talking about this more in lab today. We'll come back to that. Next kind they list here is electrical energy. Now in your book, you'll notice they do chemical energy next. It doesn't matter what order these are. Electrical energy basically deal with charges, with currents, with voltages, with resistance, that kind of stuff. That's electrical energy. We'll do that in 2 chapters, okay? Chapter 4 is heat and thermal energy, and chapter 6 is electricity and magnetism. Okay, so that's coming up later. Chemical energy. We'll do a little bit of the chemistry type stuff when we get to chapter 8, but we won't really talk too much about chemical energy. So let me just give you, well, the statement here, the energy involved with chemical reactions. Are y'all doing any chemical reactions right now?
I'm sure we are.
I'm certain you are too. If you're alive and talking, you have to be doing. You're metabolizing food right now. Whatever you had for lunch, your stomach is changing it chemically right now, okay? In fact, when it was in your mouth, your chewing it was a physical change, but the beginning with your saliva, you were beginning to make chemical changes to that food, okay? And when it got down to your gut, it continues big time. If you look at the little green leaves out there on the trees, what are they doing? They are receiving energy from the sun, and if you go over to the next column there, you see radiant energy. That's a form of electromagnetic energy, receiving that energy from the sun and using a process called photosynthesis, photo meaning light, the energy they're getting from the sun, and they're synthesizing sugars. That's really what they're doing. They're pulling up moisture from the ground, that's water, and they're pulling in carbon dioxide from the air, and between the H2O, water, and the CO2, which is carbon dioxide, they are synthesizing C6H12O6. Those are simple sugars. Fructose, sucrose, one other glucose, okay? Those are the sugars, simple sugars. Then later, other parts of the trees will take that and transform them into more complicated carbohydrates or hydrocarbons, like the pecan trees. When they start forming the nuts, those nuts are mostly fats, which are hydrocarbons. So those will go into that. The wood in a tree is cellulose, which is a very complex carbohydrate. So those trees out there are doing photosynthesis, doing chemical reactions right now. And like I said, they're using radiant energy coming from the sun, electromagnetic energy. Visible light is just a tiny spectrum, part of that spectrum, but fortunately we have a wonderful atmosphere above us, and that atmosphere repels most of the dangerous radiation. most of the radiation coming out of the sun is highly radioactive and would kill us dead, okay? Our atmosphere, thank goodness, is out there, and it's blocking most of that dangerous, hazardous, fatal radiation, okay? The only part that makes its way through is that little bitty visible light spectrum. You know it: red, orange, yellow, green, blue, indigo, and violet. Those are the colors. That's a part of the spectrum. Tiny little part that makes its way through our atmosphere. Now, that's not completely true. A little bit of ultraviolet light comes in. That's energy that's a little more powerful, stronger than violet light. Okay? Ultraviolet, good, bad, or indifferent?
It causes cancer, doesn't it?
Yes, it does. You hit it on the nose. That's what causes most of the skin cancers, is ultraviolet radiation. It causes cataracts. I've had cataracts removed from both of my eyes. If you're living and live long enough, you're more than likely are going to have cataracts removed, because ultraviolet radiation damages the lenses in your eyes, and they get cloudy, and they'll need to put in an artificial lens. Okay? Wrinkling of skin, that's caused by ultraviolet radiation predominantly. Now, those of you who are SUN sun worshipers and get out there and lie in the sun, you know what you'll be in about 50 years? Prunes, okay? Because your skin is going to be so wrinkled, and you may have a bunch of skin cancers as well. That ultraviolet, you know what a suntan is? A suntan is your body trying to defend itself. Because when your skin, especially those of us who are fairly fair-skinned, get out there in the sun, your body starts sending melatonin, I think it is, to the surface to try to block that ultraviolet radiation from damaging skin cells. That's why you get a suntan. If it can't get it there in time, or there's not enough of it, you get sunburns. That burn is from ultraviolet radiation. And if you get too much of that on your cells, that then can deform the DNA, RNA of your cells, and that's what causes skin cancers. You have basal cell skin cancers, carcinomas, melanomas. There's just all sorts of skin cancers and other things that that ultraviolet radiation causes. You don't want to do it. It might make you look sort of good now. It won't make you look good later. All that scar tissue. Okay. Now, nuclear energy, guess what? That's where the light came from in the first place. That's energy involving the nucleus and nuclear reactions. That's all that the sun and all the other stars are great big balls of nuclear reactions. Okay? Those are usually fusion reactions, where you're fusing small molecules into larger ones. On the sun, hydrogen is being fused into helium. But as a byproduct of that, enormous amounts of energy are leaving the sun. Okay? And that energy just goes out in all directions through space, and just a tiny fraction of that hits the Earth's surface, and only a tiny fraction of that makes it through our atmosphere, and that's what keeps us warm and keeps us going. Okay? Now, what I haven't mentioned there, some of that energy that does come through our atmosphere, as it's coming through, it's losing energy. Okay, now energy is never created nor destroyed, so it's not destroying energy, but it's losing that energy because the light radiation is at one wavelength, and as it loses energy, it lengthens the wavelength, and those longer wavelengths cannot get back out of the atmosphere. That's why, as far as we are from the sun, we should be too cold to support life. But because our atmosphere, again, not only is blocking the dangerous radiation, it's also acting as a blanket, keeping us warm. Now, too much of that might not be a good thing. On a day like today, if you left your car outside, which, unless it's in a garage or something, left it outside with the windows all up tight, if you were to go get in your car right now, I'm not suggesting you do this, okay? But if you were to go get in your car right now, how would it feel? About the same temperature? Very hot, exactly, because the sun is beaming down on it like crazy. Why is it hotter inside than it is outside?
Because it has no airflow, or it has a very restricted airflow, so it can't circulate and release heat.
Okay, that last part was the closest. Yeah, it doesn't have any airflow, so it can't lose it, but what it's gaining, see, the light is coming in. Light is a certain wavelength. It goes through the glass, but that loses some energy going through the glass, lengthens the wavelength, and at the bottom end of the scale, remember the violet end was the most energetic end. That's where ultraviolet comes from. At the other end is red, and below red is infrared. And infrared energy is heat energy. So that's what's happening. The light's coming in as visible light, but it lengthens its wavelength and becomes heat. The heat infrared radiation doesn't have enough energy to make its way back out through the same window or any of the windows. So therefore the heat is building up inside. Sure, there's no airflow to blow it out, but the main thing is the energy coming in as light is then changed to heat, and the heat doesn't have energy enough to make its way back out through the window again. So that's why it builds up inside. And a real serious ramification of that is in the summertime when it's really hot and that sun's really beating down. If you were to leave a pet or a small child in a vehicle with the windows closed in that kind of heat, they can die or get incredibly ill. So that's a very dangerous thing to watch out for. And a lot of daycare centers that they used to go on field trips and things like this, if they had to keep count of those kids, they didn't want a kid falling asleep, they couldn't see, leave him in a closed vehicle while everybody else was having fun, and then someone said, well, where's little Johnny? We don't know, and they went back and found him in a hot, very hot vehicle. Not a good situation. So those are some of your energy forms. This slide didn't even mention heat. That's another sort of a form of energy. So let's move on to, and by the way, your book has several pictures which are quite nice. Figure 311 is mechanical energy, that one that we're going to be dealing with, is pushing the boat through the water. The boat has energy of motion, that's kinetic energy. What is pushing that? Well, I bet you there's fuel that's being burned. And when that fuel is being burned, you're converting chemical energy of the fuel into, and that's a chemical potential energy, by the way, of the fuel into the movement of the propeller. The propeller is pushing the water. The Newton's third law makes the water push the boat, and that's what sends you and gives you the mechanical and kinetic energy of the boat. 312A is a bunch of firewood. Okay, that firewood has stored chemical energy, stored from those little green leaves, making the carbohydrates, and the complex carbohydrate called cellulose. That's what you burn in the wood stove or the fireplace. The guy in the B part there is standing on a huge mound of coal. Have any of you ever driven past Birmingport on, 369? It's just amazing to see those piles of coal there ready to be loaded, offloaded, or they've been offloaded. Huge piles of coal. That's little green leaves from millennia ago were storing the energy that got put into swamps and boglands and stuff like that, and that got deposited on top of one another until finally it became lignite and then coal. We'll talk about those a little bit later. On figure 313, you see solar cells. It's a demonstration solar cell array that converts radiant energy, that light from the sun, electromagnetic radiation, into, and that says, producing an average of 200,000 watts of electrical power after conversion, and that's probably in Arizona. That's what it says there. Now, I wish that they had figure 314 on the slide set. That's what I was just talking about in the energy spectrum. Okay? That's what they were talking about here when they said visible light is just a small part of the full spectrum. Let's start at the upper end. The high energy radiation is the high frequency radiation. On the other hand, it's the short wavelength radiation. And as your frequency goes down, the wavelength goes up. So the high energy is a high frequency, low, small wavelength radiation. And up at the top are those gamma rays. Gamma rays will kill you. Okay? Do you remember, I don't know, y'all may be too young, it was a few years ago that a couple of former Russian spies, or at least one and his daughter or something like this, were having a meal in a London pub or out on the street or something like that, and he got very ill, and she did too. Some Russian agent had dropped some radioactive material into their food somehow, into the drink, and it was a violent death. It went over a long period of time, several days, incredibly painful. Gamma radiations kill cells. And by ingesting those gamma radiations, it was killing them from the inside. But gamma radiations are so strong, such high energy, they go right through you. I guess y'all know about Hiroshima and Nagasaki, right? Okay, those were the two places where we dropped atomic weapons at the end of World War II. Many of the people killed then, and I mean hundreds of thousands were killed by single bombs, okay? Many of them were killed by just the blast, the incredible amount of heat that came out of that. Nuclear reaction, now that was a fission reaction, not nearly as powerful as a fusion reaction, but still way more powerful than any other bombs ever dropped before. But a lot of people were killed by the heat. But those that were far enough away that the heat didn't get them, then the gamma radiation did, and it's not a rapid kill. It's a long, slow, miserable process. So those gamma rays destroy tissue, and they go right through you, so they destroy tissue on the outside, on the inside, everywhere. Next after that is X-rays, and you think those are good things, and they are, but they enable their high energy radiation that sees through or penetrates through soft tissue but gets blocked by harder tissue like bones. Gamma rays go right through. But if you've ever had an X-ray, say in a dentist's office or in a doctor's office or wherever you may have had it, if you notice, does the X-ray technician stay out there with you? Anyone had X-rays?
No, they're...
Where do they go?
Yes. No.
They're normally in a separate office through like a big glass pane.
Yes, through a very dark glass pane. That dark glass pane is leaded glass. It has lead embedded in the glass. Lead will block most X-rays, okay? And I bet you that wall in between you and them, that's got lead in it too. They are protecting themselves as much as possible. Because that short burst of X-rays you receive, you know, hopefully that's not going to do any damage. It's just enough for them to get a picture. But those guys are in the room and gals are in the room all week, taking X-rays every day. They could get exposed to way more than they need, so they get as safe as they can be. And I bet you every one of them is wearing some type of a badge that records the amount of radiation they've received in a month. And every month they have to mail that into the some type of an office somewhere in the state or the business where they're working, and someone's reading that to see if they got overexposed during that month. If they did, they are home. They cannot go back until they've had enough time to get over that exposure. So they're very careful not to. Then you see that big wide band of ultraviolet radiation, and you'll notice on some of your sunglasses or sunscreen, they'll say UVA and UVB. I don't know which is which end of the scale, but both of those, it's a wide band of ultraviolet radiation. And again, our atmosphere gets most of that, but not all of it. Look how small the visible light spectrum is. That little bitty window is all that comes through our atmosphere, undeterred. Thank you, atmosphere. But then once it gets inside, some of that gets linked into infrared. That's our heat radiation. And what's the worry these days? Before the coronavirus came around, what was one of the big scientific discussions and topics that most of the nations were somewhat concerned with? Global warming. What is happening there is different components of our atmosphere contribute differently to lengthening that energy, the wavelengths, in other words. And some of the compounds that do that the best are the carbon compounds. Methane gas is a serious global warming element. Carbon dioxide is. And there's some others as well. And the more methane and carbon dioxide we release into our atmosphere, the more we retain extra energy from the sun. It can't escape because that absorbs it. So we are getting warmer and warmer. In fact, I think the highest global average temperatures, I'm just making a guess here, probably the 5 or 6 highest global average temperatures have all probably been in the last 10 years. I mean, that's unbelievable that you'd have that many record high year after year, maybe skip a year and then the next year. Okay? Then under that is microwave radiation. That's both in the microwaves that you heat your food in, but it's also what sends your cell signals. That's microwaves are carrying this message from me to you right now, especially if you're on a cell phone. Okay? Then you have your, and FM just means frequency modulated, but these are your UHF radiation, ultra high frequency radiation, radio radiation. It's not ultra high as in gamma rays, but ultra high for radio radiation. Then there's a blank band there, and that's, I think, where the citizens bands are. Things like police departments, fires, things like this. The old CB radios used to use that band. Ham radio operators, I think, do. And then you have the kilohertz range, which are your AM radio stations. And then you have the longer radio waves that are very low energy, but can sometimes travel long distances. Okay, that's an important figure. I wish it was in the slide set. So let's go to energy conversion. This is on the bottom part of the right-hand column of page 73. We've already been hitting some of this. Any form of energy can be converted into another form. Now, I don't quite agree totally with that statement. Now, you'll find out why in a minute. I would say most forms of energy can be converted into another form. And here they use that flows again. Energy flows from one form to another in natural processes, like the trees photosynthesizing light and storing it as chemical energy in sugars or starches or carbohydrates and hydrocarbons. Okay, those are natural processes. One other example, and this would have been the next lab that we would have done if we were on campus. Well, here's the guy bowling again. We saw him last week. He's still bowling. He hasn't released that ball yet. He's done work on the bowling ball by lifting it and then as soon as he quits lifting, he starts pushing it down an arc until it gets to the floor. It's changing its potential energy, the energy of position between here and the floor. That's a potential energy, plus the energy the arm gives it as it pushes it. So the ball down here has totally kinetic energy. It's no longer changing position. We mean vertical position, working against gravity. Up here you're doing work against gravity. And now it hits the pins. Now it gives the pins kinetic energy. It loses some, but you know it bangs into the back. You hear it every time it does. And the pins go flying as well. Usually not too many of them if I threw the ball. Okay. Now, their example next is the pendulum. And here is a rendition of what a pendulum is. It's usually a weight or a mass at the end of either a long cord or a long rod. It can be either one. I don't quite, maybe it's just an optical illusion, but it looks like to me this line here is longer than that. That line should be the same length. And this should be a circular arc that's formed here. Okay? Looks like they got theirs a little long up there. But when you raise that pendulum to a certain position, you're giving it potential energy. You're doing work against that weight as you lift it that height above that height above its lowest energy level. That is the zero energy level, the zero reference level, as low as that pendulum can go in this problem. Okay? So you're lifting it, and this is its potential energy relative to the zero reference point, okay, or reference line. Up there, when you're holding it there, it has no kinetic energy because it's not moving, okay? All of its energy is potential energy. You release it, and now it starts losing potential energy because its height is going down, but it starts gaining kinetic energy because it starts speeding up. So at some point down there, in fact about midway between maximum height and minimum height, it will have about 50% potential, 50% kinetic. It continues going down until it gets to the lowest point it can go, because the string is only so long, or the rod is only so long. So now it can't go any lower. It's lost all the potential energy it had because it's at the zero reference level, zero potential energy. All of its energy is now kinetic energy. But remind me, what is the sum of potential and kinetic energy? Anyone remember? It's on the screen now. Mechanical energy. Perfect. Okay? The mechanical energy of that pendulum is always the same. It's just that all of it is in potential up here. It's about 50-50 here. It's all kinetic here, but it's always mechanical. And it never changes. Because what is that going to do once it passes this point? It's going to head right back up until it reaches here. It will never go any higher than there. It can't, because that's all the energy it has. Now the only way it could, if rather than releasing the ball from this first point, you threw the ball from that first point. Because then you would have given it initial kinetic energy. It wouldn't have been 0%. It would have some. So then on this side, it keeps going up until all that kinetic energy becomes potential energy. It stops and then swings back again. But we're not throwing the ball. We're just releasing it. Okay? Does that make sense?
Yes, sir.
Okay. When they say the total is total mechanical energy is the same throughout the experiment. Okay? Now, any questions? Okay, here it is. The total energy of the pendulum is fixed. It's the sum of kinetic energy plus potential energy, and that sum is called mechanical energy. For some reason my pen is not writing. Mechanical energy. That is fixed. It's constant. it's conserved. It's not lost. Kinetic energy, constantly changing. Potential energy, constantly changing. Mechanical energy, constant. Any questions?
No, sir.
Okay. Now we move from energy conversion. Okay, let's see. We've got a few other things here first. Figure 315. That's a really big rendition of a steam turbine used in power plants. They're also used, probably not that big, in a ship. What you do is heat water to superheated steam and fire it through a steam turbine. That's what propels a big ship, like a Navy ship, forward. Now, there's a few of the smaller naval vessels who actually burn natural gas or some sort of liquid. Actually, what they call it is Navy distillate. It's sort of like a kerosene type distillate, and burn that, and that's what is the hot air that's going through the turbine. But usually steam is cleaner and doesn't wear out the turbine blades as fast as something like a exhaust would. Okay, but some are just run by the explosive gases, the exhaust gases. All right. Now, before we get to energy conservation, I wish they had this here, and this is as good a slide as any to put it on. Let's see. Let's put it here. I want to give you a couple of equations they have in the book, but they didn't put on the slide set. So let me clean this off and give them to you here. Well, let me go back. Right here. Here, the pendulum mass or weight has 100% potential energy. That is, does anyone remember the formula for gravitational potential? My pen's not writing well. Potential energy. Anyone remember that formula?
Not off the top of my head, I'm sorry.
What was that? Anyone remember it? Since it's gravitational potential energy, I'll give you a hint. The acceleration due to gravity is in it. Ring a bell? Well, the energy would depend on mass. For instance, a bowling ball is a lot more energetic than a ping pong ball, right? So mass is in it. Does that ring a bell? MGH, perfect. Okay, with 2 clues you get 7 points. No, never mind. Okay, that's supposed to be an H2, but my pen is not writing worth a 2. Okay, MGH. At the bottom of that swing, the same energy is now all kinetic energy. Does anyone remember the formula for kinetic energy? Anybody? I don't. Somebody said something while I was talking. I didn't hear it. Was it 1/2 mass times velocity squared? Okay. Now, when it's all kinetic energy, all that mechanical energy is in that form. When it's at the top, all the mechanical energy is in that form. So that's the same energy at top or bottom. It's just in different forms. So if you set these two equal to each other, and this is what they do on page 74 in the text, you have MGH. I don't know why they put it in this way. I'm going to do it the way I was going to do it. They're backwards here. I mean, it doesn't really matter. Okay. 1/2 mv squared is equal to mgh. Now this is 1/2 mv squared. That's at the bottom. This is at the top. Okay. All the energy is in one of those two forms. So let's find out what the velocity is at the bottom. Okay. You know what the mass is. You know what acceleration due to gravity is. You can measure the height at the top. It's really hard to determine what that velocity is at the bottom. You have to have a speed gun and you have to operate it just perfectly, and you still only get an estimate answer. So let's solve for v and find out what the final velocity is at the bottom. What would be the first thing you would do to isolate the v? What's the least attractive thing in this problem, especially on the left-hand side? Y'all like fractions?
You said you had to divide, right?
Okay, you do have to divide something, but let's first multiply by 2 to get rid of that 2 in the denominator, right? I don't like denominators that much. Y'all like fractions. I don't care for it that much. So there, I got rid of the 2 in the denominator. Now we need to divide something. What do you suggest we divide to isolate the v?
V squared?
No, don't mess with that yet. What is in the way here?
M.
M. Let's divide out the m. Get rid of it. Okay? Now here's the interesting thing. The m goes out here, but it's the same mass over here too. It goes out there. So the velocity has nothing to do with how heavy the mass is on that pendulum. Absolutely nothing to do with it. Okay? So now we have v squared is equal to 2gh. Well, you know, frankly, I don't care what v squared is. I want to know what the velocity is. So how do we undo a square? Anybody? What operation undoes a squaring operation?
Square root.
Square root. You're absolutely right. Take a square root of both sides. We're only going to take the positive square root, by the way. Well, square root of v squared, this undoes that. I can't get my pen to write. Okay? So you're left with just v on the left-hand side. On the right-hand side, the square root of 2g. All right. That's the formula they have near the bottom of the right-hand column on page 74. V final, they call it V final, is equal to the square root of 2gh. The mass is not involved at all. We'll see that in today's lab too. All right. With that in mind, let's go to example 3.9. So let's back off 2 places and erase my ink. Oh, I should have asked, did anyone need that any longer? Sorry. Say again? I can't hear. I could.
This is Takasha talking.
Oh. Okay. Okay, sorry, my screen says my internet connection is unstable. Was I getting scratchy then?
Okay, Dr. Fowler.
Yes.
This is Takasha Stevenson. I'm just letting you know.
Oh, okay.
I was trying to give you a break to stop talking, so you did, so I'm sorry about interrupting.
Okay, I couldn't hear. Say again?
I was waiting to give you a break to stop talking, but you did, so I said I'm sorry about interrupting.
No. Good luck with getting me to stop talking. Okay. All right. So, anyone else come in the class? Good class attendance today. We're right now only missing Anaya, and we haven't had her since we moved to virtual class. David was here in class this morning, but he's not this afternoon. I had him for trig class. Mrs. Lewis we haven't seen since we've gone virtual. If anyone has any way to get in touch with these folks, please get in touch with them. I try sending emails and stuff, but I'm not getting any response. If you have some way to get in touch with them, please do. Zach we haven't seen since we've gone virtual. Gunnar had been here, but he's... Oh, is Gunnar here?
I'm here.
All right, good. See, I hadn't heard from you. Okay.
Microphone's not good on this computer.
What's that?
The microphone's not good.
Oh, okay. My hearing's not good either. But the also you see my screen, because I have so many applications open, Screencast-O-Matic, PowerPoint, Zoom, and everything else. I only see two names at the top besides mine. And I don't know why those two, but I only see two. They sometimes change, but I don't know why they don't rotate. But Drew, we haven't seen since we started doing virtual. Capri, we haven't seen since we started doing virtual. Lydia has been in touch, but she hasn't been in class, so she's been doing the work, or at least some of it. So she may be working now. I think she's in healthcare or something. Katie we'd never have seen, so she may be going to be removed from the class. And it looks like everybody else, we have pretty good attendance today. Way to go. All right, energy conversion then. No, we finished that one. No, we're going to do the example. 3.9. A 1 kilogram book, 1.0 kilograms. What's that a measure of?
Weight.
No, it isn't.
Mass.
Mass. This is mass. Weight would be Newton or pound. This is kilogram is a mass. Now, my pen is doing weird things. Rather than writing stuff, it's drawing straight lines. Okay? So it's 1.0 kilograms. Okay? Is the mass. Falls from a height of 1.0 meters. What would that be a measure of? Now this is mass, that's a parameter. This is meter, that's a unit. Don't get those confused. What is your 1.0 vertical distance called? Think of our formulas, especially that potential energy formula. Any ideas? Are you scared of being up on a roof? Height. Pretty good. Okay. What is its velocity just as it hits the floor? So we're looking for a velocity just as it hits the floor. Ring a bell of a formula we just had up here? If you called that V final just before it hit the floor, it was just on your screen.
You said V equals the square root of 2GH?
The square root of 2GH. Now, wait a minute. We aren't using the mass. Is the mass important? Not as far as velocity is concerned. All we have to do is the square root of 2 times, what's G?
9.8.
9.8. What units? Numbers are no good without the units. Meters per second squared times the height, 1.0 meters. Okay? Well, I can do that one in my head. I hope I can do it right. That is 19.6. And then when you multiply the units too, that would be meters squared per second squared. Okay? Now, I can't do this one in my head. The square root of 19.6. I can tell you it's between 4 and 5, but I don't know where in between 4 and 5 it is. You want to do that on a calculator? 4. Let's just round it to 4.4. And when you take the square root of the number, you also take the square root of the units, which would be meters per second, which is a great unit for a velocity. So it's 4.4 meters per second squared. Okay? Now, I didn't mention, I should have, the book falls from a height. Okay? Falls meaning the initial velocity was just like dropping, releasing. The initial velocity was 0. You didn't throw it from the height. If you had, you can't use this formula because this only works if it's all potential energy at the top, all kinetic energy at the bottom. Okay? Now, in your book, it's just a minor thing, but they got the units wrong, or at least in my book they did. They said 4.4 meter seconds. No, no, no. It's meters per second. I don't know who the graphics guy was, but he got it wrong. Okay? Is it wrong in your book as well?
Yes.
Yeah, okay. Correct it if you want to. All right. Do I need to leave this a little longer, or has everybody got it?
Got it.
Okay. Whoops. So here I'll erase, and let's do 3.10. Example 3.10. This time, what is the kinetic energy? This is what we're looking for. Of a 1.0 kilogram book. Ooh, it's the same one we just had. Okay. It was mass of 1.0 kilogram, and the H was 1.0 meters. And we just calculated the final velocity of 4.4 meters per second. Okay. Now that's what they want you to use in this problem. Okay? They want you to do this. What is the formula for kinetic energy? Several people have given it to me already today. You should remember it.
KE plus PE.
It's what?
Is it KE plus PE?
No, that's mechanical energy. 1/2 mv squared. Now that's the formula they want you to use. And it is the correct formula. I'll tell you a problem with it in a minute. So it would be 1/2 times the mass, which is 1.0 kilograms, times velocity squared, 4.4. Now, does anyone remember any more digits that were on that? I thought someone said 4.42. Was that right?
Yeah, it was like 4.427.
Say it again.
Like 4.427.
27? Is that what you said? Okay. Let's use, if you still have it on the calculator, use it and get that number and square it. And that was meters per second. Okay? So this will be, I'm just going to change this to 0.5 kilograms, because 1/2 of 1 is 0.5. Someone punch that in and square it. Multiply it by 0.5 and see what you get. We know what that was. This was 19.6, wasn't it? When you squared that? 19.8? Yeah. No, it was 19.8. 19.6 meters squared per second squared. When you squared that, that's what you took the square root of. So I know that was 19.6 meters squared per second squared. I can do that in my head. Not that I squared that, but I remembered what it was when we took the square root. So what does that give us? Half of that would be 9.8 meters, kilogram meter per second squared. Okay? That's ugly units there. Let me get that cleaned up. Now, what I'm about to say is, I think they did it really dumb. Okay, I'm sorry. It's meters squared per second squared. Which, by the way, what is a kilogram meter squared per second squared? Anyone remember what's that again? Joule, exactly. Women remember that, didn't they? Okay. In the book, they had 9.7. But I knew it was 9.8 because I remembered this is what the square of this was. But you see what the book did? They rounded this to 4.4, and when they did that, they lost some precision. So when they squared it, they got something less than 19.6, and that gave them something less than 9.8. So it really was 9.8. How did I know that? Because the initial kinetic potential energy was mgh, and G is 9.8 meters per second squared. So mgh is 9.8. That's in joules. So the book really did it a little dumbly there. Their insistence on rounding off made them get off by a decimal point. But you know what? I'm not going to count it wrong for them. Okay. They can get full credit. Okay, let's go to energy conservation. All right. Now, we said this about mechanical energy, and that's pretty much true, but it's never completely true. We said mechanical energy was always constant. You know it's not. If you had that pendulum swinging back and forth, after a while, it's going to slow down. After a long while, it stops. Why? There's some friction up there at the pivot point. Or there's some air resistance down here. Both of those are examples of friction. And when you have friction, you lose energy. You have low-level heat created. And remember back when we had this slide? It said any form of energy can be converted into another form, and I wanted to say most forms. The reason I said that is most of the time you can't convert that low-level wasted heat energy from friction into any other form. Maybe you can, but most of the time you really can't. So energy is never created nor destroyed. However, it changes form so rapidly it can be converted from one form to another, but the total energy remains constant. What you said? Didn't I just say you lost some to the heat? Well, guess what? Heat is a form of energy, okay? So you haven't lost it. It's just wasted, but not lost. And one example they give is free fall. If you remember that from last chapter, that's when you drop something from rest and let it fall due to gravity alone. Again, you're ignoring air resistance then, okay? So let's see their slides first. Oh, here it is. Now they do this. I thought they did it somewhere. The potential energy lost when you drop something is equal to the kinetic energy gained at the bottom, and that's where our formula came from. mgh is equal to 1/2 mv squared, v final squared. When you multiply both sides by 2, divide by m, you get, and take a square root, v final is equal to the square root of 2gh. Okay. They do this under energy conservation. The book did it under energy conversion. So that's why it was in a different place. Kinetic energy, potential energy is changed to kinetic energy as the object falls through some height of h. Okay? Now, here's the figure above that formula in the book, figure 317. If you have a 10-meter height and you're going to release it, not throw it, release it. So its initial velocity is 0, and that's exactly what they say here, because you released it, you didn't throw it. Okay? Your potential energy is mgh. They didn't give you the mass, but I'm assuming from what they have here, the mass was 1 kilogram, because 1 kilogram times 9.8 times 10 meters will give you 98 joules. Okay? Because the initial velocity is 0, the kinetic energy initially is 0. When it's halfway down, now the h is now 5 meters. Mass of 1, g is 9.8. 9.8 times 5 is 49. And the velocity now is 9.9 meters per second. You don't know that. You know it because the kinetic energy, because your total mechanical energy here is 98 joules. It's the sum of these two. And since down here, when you're at 5 meters, you know potential energy is 49. That means the rest of the, because mechanical energy is still 98 joules. And if 49 of those joules are potential, the other 49 are kinetic. If the other 49 is kinetic, then you can calculate the velocity. Or you can use this formula here. The square root of 2g, h you put in here as 5 meters. You plug that in, you'll see you get 9.9 meters per second. Then at the very bottom, you will get your potential energy is zero because your h is zero. This is where you measure your height from, okay? That's one thing we might do differently in the lab today. You get to choose where your zero potential level is, okay? And wherever you choose that, that will determine your calculations. They'll all come out the same, but it will make a difference in your calculations. Here, your velocity, here halfway down, you didn't get half the speed. You got more than half the speed because it doesn't take it as long to fall that last 5 meters. This was pretty slow up here. It's already going pretty fast down here. And your kinetic energy is all 98 joules. Because all your mechanical energy down here is still 98 joules. Energy is conserved. The total energy in this case is mechanical energy. Now, if there had been air resistance, whatever you lost due to air resistance, that would be lost to a little bit of heat. That would decrease your kinetic energy at the bottom, which you know is usually what happens. Any questions on that? Okay. Now, the energy transfer mechanisms, how energy does get transferred, is either from work or from heat. Now, that's a broad generalization. But how do you change the energy of that bowling ball? You do work on it. You push it. You lift it, giving it more potential energy, and you push it when it goes down. That's how you give more, make the energy transfer mechanisms work. Or, like in your car, that explosion in your cylinder is what pushes the piston up, which is doing work for the car. You're transferring the energy from a stored chemical energy in the fuel to a massive amount of heat energy all of a sudden, and that gives you mechanical energy or kinetic energy of turning the wheels, ultimately. Make sense? Anyone need this a little longer?
No.
Was that a yes or no? Okay. All right. Then the flow of energy. Again, this must be important. They've only said it 3 or 4 or 5 times. Energy is never created nor destroyed. However, energy can be converted from one form to another, to another, to another, but the total energy remains constant. Okay? Now, again, this gives a very simple illustration of what we talked about before. Nuclear energy from the sun makes its way across space, hits our atmosphere, and a little bit of that electromagnetic radiation comes in the form of light energy. That's radiant energy. It hits the little green leaves on the tree, making stored chemical energy in those chemical bonds of sugars and fruit, nuts, whatever it's producing. We consume those. Boy, they're pretty tall, aren't they? Almost as big as a tree. We consume those, and by our metabolism, we make more chemical changes, producing heat. Have you ever thought about it? What's your temperature? Anybody know it? Approximately? 98.6 Fahrenheit if you don't have a fever, right? What's the temperature of the room you're in? Anywhere close to that?
70 degrees or so.
Yeah, 70 degrees or so. That's a 28, nearly 30 degree change of temperature. Why are you so much hotter than the room? you're constantly chemically breaking down that heat, the chemical energy from the food, and changing it into heat. That's what keeps us warm. That's what enables us to move, to see, to hear, to do all of our functions, the heart to beat, the muscles, everything happens because we're constantly converting chemical energy to other forms of energy. Now, some of those forms of energy, how does the signal from your brain get to your heart to tell you to beat? Or get to your ears to hear what you're saying and interpret that? Or from your eyes to read what you're reading and interpret that in your brain? Anyone know how that happens? You are an electrical machine. You're also a chemical machine because you're consuming food and chemically converting that, but you're also an electrical machine. Your brain is sending out messages constantly through a neural system. Your nerve system is carrying electrical impulses, okay? And what you see, you hear, you sense, that's being fed back to the brain. The brain is breaking down those signals. You're an amazing machine, by the way, okay? You can do all that. And you can get on that bicycle, both those bicycles, and change that to mechanical energy, or especially when you hit the brakes, then you're going to be producing heat in the brake mechanism back here, but also on the surface down here, and that wasted heat is going to make its way back into the atmosphere, heating up the planet. There you go, and did it again, huh? Now, it was an ugly, ugly time in our history, but it hasn't been that long ago. How did we execute prisoners before we got chemical injections?
Hanging, the guillotine.
Okay, not that long far back, more recently than that.
Firing squad.
Okay, more recently than that. Alabama had one.
Electric chair.
The electric chair. How did that kill somebody?
I think it's kind of obvious.
Okay, well, it may or may not be. It disrupted the electrical system of your body. It suddenly threw too much current and too much voltage at your system, which is very carefully controlled. It shut things down completely because it overrode your electrical system. Just like the chemical injections, they disrupt your chemical systems. Then they put a whole mix of things in it. It's a pretty gross thing to talk about, but that's what you're doing. The chemical injections disrupt your chemical system. The electric chair used to disrupt your electrical system, and that shut your body down. The hanging disrupted the breathing, well, let's not get into all those. Okay. Firing squads, yeah, okay. Let's see, is that? No, it's not quite. Energy sources today. This is going into 3.4. This is on page 76 as you're following in the book. Now, our figure on the slide is older than the one in the book. So let's look at the one in the book. If those who don't have this one in the book, I will fill you in on it. Our energy sources today, let's first look at what they say here. Primarily, in the not too long ago past, it was primarily wood that we burned as our energy source. We burned it actually in the early locomotives. They would load up on wood, feed it into the furnace, heat the water. The steam would be what they used to move the train. This was before they had automobiles. And even some of the early cars were fed by something like that too. Then they moved to petroleum. Petroleum, with more industrialization, this is what they went to. Nowadays, they're actually going away from petroleum, trying to get more to natural gas. Okay? So other things are happening. So all those that we talked about there, wood, coal, petroleum, natural gas, all that can be traced back to the photosynthesis of those little green leaves on the trees but it could be those trees that that were in existence a millennia ago or longer, centuries ago, millennia ago or longer. Okay? And we'll talk about how that came about a little bit later. Now, the usage of that, well, let's go with the slide over here. I'll give you the new figures from your text. Petroleum is now 36%. Now, I'm not saying we use less petroleum. We probably do. I hope we do. But it's a smaller percentage because we're using more energy all the time. Okay? Coal used to be 21%. That's way down to 18%. And I bet you nowadays it's even less. Okay? Natural gas in your book was 27%. And the slide set was 23%. This has gone up to 27%. Okay? Much more higher percentage. One of the reasons here, we've gotten way better at capturing natural gas. Some of the things you hear about in the news, the processes of fracking, and things like that, they're able to use that better. So whereas petroleum and coal are down from what it was when the slide set was done to when the book was done, and I bet you they're even further down now. Natural gas has gone up and probably continues to go up. Nuclear it's 8% in both places. Okay? Does anyone know why that didn't increase that much?
Because nuclear power has gone out of style.
And why? Any particular reason?
Because it scares people?
Yeah. And you remember the specific incident that made it scare people?
Chernobyl?
Yeah, well, that's part of it. Chernobyl was over in the Soviet Union at the time. It's now part of Ukraine. And that really scared people. But you see, it wasn't just what happened over there. We had an incident at 3 Mile Island, which was here in the U.S. It wasn't nearly as serious as Chernobyl, but it really was scary. And since it did happen here, that really convinced people. In fact, I think at least a couple of decades went by that they did not authorize a new nuclear power plant anywhere in the U.S. Okay. Now, that didn't happen worldwide. Japan went more and more toward nuclear. I think France went more and more toward nuclear. A lot of countries did. What has put a halt to those, pretty much? Anyone ever hear of Fukushima? I probably didn't pronounce it well. Fukushima. It was
a power plant in Japan that got flooded.
Yeah, it got flooded by a tsunami. And you see, unfortunately, nuclear power plants especially, have to be built very close to water because you have a lot of excess heat that you have to get rid of, and water is a great way to get rid of heat. You know that from your automobile, right? How do you get rid of excess heat in your automobile? Some of it goes out the tailpipe, but really not that much. Where does most of it go? Through the water system that goes through your radiator. And then your fan is blowing air through that, cooling that off constantly. Whether you're using that in the cabin or not, you're probably not this time of year, but it's just blowing into the atmosphere, okay? That's how we cool things, with water, okay? And that's what they were doing there. Well, unfortunately, Japan is an island, and the best source of water is right there on the ocean. Well, for those who were in my Physical Science 111 class, what is the Japanese island chain? Anyone remember? Say again?
It's volcanic.
Yes, exactly. It's near a fault line. It is on a fault line. So all those nuclear power plants were right on, pretty close to a fault line. And when that had a shift, which was the earthquake that caused the tsunami that flooded Fukushima, that's what happened. And basically that nuclear meltdown was probably as bad and maybe worse than 3 Mile Island, but the Japanese had been so incredibly careful in building theirs, they were able to contain it. Where the Soviet Union, they were just interested in building things fast and furious, and they didn't meet all the safety precautions. So that's why it was such a disaster. And let me tell you just a little bit of how serious that was. And this is just a minor thing, but if someone will look up for me right now when that meltdown occurred, Chernobyl happened. I think it was probably in the 50s or 60s. Someone get that on your phone right away?
I think it was in the late 80s.
Oh, late 80s. Okay, that may be true. Okay.
April 26, 1986.
86. Okay, 86. Okay. Now, about, I'd say no more than 5 years ago, maybe, I had a student in one of my in two of my classes actually, Math 100 and later 112. He had been adopted from Ukraine. He was in an orphanage in Ukraine because he was born with only one arm. Why? Because his family, his parents, had lived somewhere close to where Chernobyl was. It had messed up their DNA. When he was born, they basically threw him away, sent him to an orphanage. And fortunately, he was adopted by some really great people here in the Birmingham area, and he was trying to become a physical therapy technician so that he could help other people who had physical handicap. I know this because before he even was in my class, I knew his story because I'd read about it in the paper, and I had friends that knew the people who had adopted him. Just an incredible thing. He couldn't have been much more than 20 years old when he was in my class about 5 years ago. So let's just say that was 2012, say. So 20 years old, that would be 1998. No, 1988. No, 1998, I was right. Okay, am I? Yeah, 1998, or 92. So Chernobyl had happened basically about the time his parents were born. And yet it had done enough damage to them that 2 generations later, you were still seeing negative effects of Chernobyl. Not a pretty picture at all. Okay, let's go on. Now, in the book, they don't separate biomass, hydro, and other geothermal and solar. They just lump it all into renewable. And renewable in the book was 9%. If you add these together, you get 6.5 and a half. That would be 7%. So it went from 7% to 9%. Boy, that's not a very big jump. It is a jump, and it's a jump in the right direction, but it's not a very big leap at all. We got to do better. I'm sure today we're a lot better than that. I think there's a lot more wind farms, like you saw in the picture. I thought I saw them in the picture, but I don't see it now. It was somewhere earlier in the chapter. You have a whole lot more of those these days than you used to. I think you have a fair amount more solar than you used to. And they're trying to do things like geothermal and other things. But anyway, that's the breakdown. That's the update from what we had before. These three are grouped together. All right, what are the uses? At least when the book was done, about 1/3 of it is used for heating. That's heating of homes, heating of businesses, heating of things. Okay? About 2/3 are burned in engines and generators. Engines like car engines, truck engines, boat engines, engines that run factories and things like this, or engines that create the heat from that is used to generate electricity. So a lot of it is used for a variety of sources there. Okay? The more industrialization, the more the 2/3 have grown, probably the 1/3 has moved down. Okay. Let's look at each of those energy sources sort of separately. Petroleum basically has some oil, and that oil, believe it or not, comes from rock. Now, I know the pictures out in Texas and things back in the oil boom, drilling into the ground, and suddenly you get a gusher. And maybe in some places you still find that. I don't think so. I think most of those gushers have gushed out. So now they're getting most of the oils from oil-bearing rock. Okay? Now, where did that oil come from? Well, it started with organic, meaning materials coming from plants, some animals too, but mostly plant, organic sediment, things that were living sediments that got buried deeper and deeper and deeper and deeper into bogs or swamps or other things like this. But it wasn't just the fact they were being buried, they were being processed by bacteria. Now, there's two major types of bacteria, and this is a gross overgeneralization. Some of these are what we call aerobic, meaning the bacteria that live in air, but many bacteria are anaerobic, meaning they don't get their oxygen from the air. They get their oxygen from other sources. For instance, you have a whole bunch of bacteria that live in your gut, and they're not all bad. They're mostly good bacteria because they help process food that your body doesn't process and breaks it down so you can either use it or get rid of it. Okay?
Is that prebiotic or probiotic?
That's basically what you're talking about when you're talking about those, is the probiotic idea. Now, sometimes you may be just feeding those bacteria, or maybe you're actually ingesting them. I don't know what goes into all those things, but that's what they're talking about. That's exactly what they're talking about. Well, these kind of bacteria, some like it, are underground, and all this stuff that's gotten buried, they need to get their oxygen from some source. Well, they get it from the carbohydrates. Remember that? Carbo means carbon. Hydro means hydrogen. The drate, that means oxygen. Okay? So the carbohydrates, they contain all three of those. Okay? Well, if those got buried, and that's what the leaves and the wood and sticks and stems and everything else are mostly carbohydrate. So these bacteria basically use the oxygen out of there, leaving behind hydrocarbons, which is what petroleum and coal and all these other things are. But it's not just the bacteria. There's also all the pressure of that overburden that's been stacked on top of it, and that pressure generally produces high temperatures. So it's a combination of the bacteria doing their part, the pressures and temperature. Over time, the chemical structure of those things change and become petroleum. You'll see the same procedure when we're talking about coal. Now, the natural gas formation is very similar, except it's even at higher temperatures. So it's not a liquid then, it's actually a gas, okay? And it's formed the same way. Now, those gases are sometimes stuck, held in gas-bearing rock, I guess you would say. And that's what the fracking processes are doing. They're trying to chemically alter that natural gas-bearing rock to release the natural gas, and they try to capture that, and then that's a really grossly simplified way of explaining what's going on. So the petroleum and natural gas are often found together. In fact, remember when those old wells would spew up into the air? If you watch those old movies, what's spewing them into the air? Well, number one is some pressure, but the other thing is the natural gas. Well, they're trying to capture the petroleum, but back then they weren't even caring about the natural gas. It entered the atmosphere and was sort of wasted. Nowadays, we try to capture all that we can because that burns much cleaner than petroleum does. But supplies are limited. Right now, about 25%, well, when the book was written, about 25% were from offshore wells. We had just about drained all the sources we could from easily to access parts in the U.S. and other countries. So we have gone offshore trying to capture things from there. And think about it, there's a lot of sea life that has died in the bottom of the ocean and accumulated over time. So there's probably quite a bit of petroleum down under those, but that's pretty hard stuff to get to. Do you remember the Gulf oil spill? Were y'all alive then?
Yes.
Yeah. I didn't know the Gulf of Mexico went down as far as 1 mile deep, but that well, where they were getting that petroleum from, was from 1 mile deep. And at that depth, you're at totally black conditions. No light gets anywhere close to 1 mile deep, and incredibly cold conditions. So everything they were trying to do to stop that breach that was pumping all that petroleum out into the Gulf of Mexico, it was having to be done a mile down and at extremely cold temperatures. They couldn't see, it was a mess. So I bet you some of our offshore drilling has slowed since that happened. Now they say here over 50% of our petroleum is imported. I think that the U.S. finally has gotten so we are providing more than 50% of our own petroleum and natural gas, mostly because of the fracking. Okay, so that has probably changed over the years. All right, coal. Again, accumulated from plant and maybe some animal materials. Again, processed over time. Time is very important in both of these. Again, by pressure and temperature. They left off the bacteria. They're involved with it too. But this time it doesn't go to a liquid. This goes to from a substance called peat. I don't know if you've ever heard of that. We don't have that I know of very much in this country, but if you've ever read much from England and I think Russia and many other areas like this, peat was what they used to burn. They would go out and get a swampy type area where a lot of organic matter had accumulated, and over time, probably not that long a time, maybe a few 100 or 1,000 years or so, it was into a form they called peat. They would burn that. It was pretty nasty, but it was a good fuel, a decent fuel. But if you leave it down there, it then changes to a mineral called lignite, and then the lignite ultimately goes to subbituminous coal. Now this is the good coal up to bituminous. That's the best coal. A lot of the coal that we have here in Alabama, unfortunately, is anthracitic coal, which usually has a lot more sulfur in it, and it's just dirtier coal. So what do? We dig it up still, and we send it down at, I don't know what Birmingport is doing, whether they're shipping it in or shipping it out. I'm guessing they do both, and they send our coal downstream, and that gets to the Gulf of Mexico and goes to South America and those kind of countries. It's pretty cheap, but dirty coal, making a lot of pollution, and we are importing from who knows where. I'm thinking mostly from Wyoming and places, the good, rich bituminous coal, which is still pretty dirty, but it's not as dirty as anthracitic coal. Well, guess what? We all live on the same planet, and whether they burn this in South America or they burn it in Birmingham, it's still going to enter the same atmosphere, and it's going to dirty the same atmosphere. All right, here's the problem with coal. Now, are any of you from coal mining families? I don't want to get anyone upset. Yes. You are? Okay.
Yeah, but it's fine.
Okay. Is that Kurt saying or who?
Ian Mason.
Oh, okay.
My grandfather and his father were both coal miners.
Right. And it was a hard life. And it was a dangerous life, not just from collapsings and things like this, but from things like black lung disease and breathing too much ash and stuff. And then down there you could be exposed to all sorts of other things. You could have explosions. It was a hard life, and those people kept us going for a long time. But the problem with coal today is, and we've used most of the good coal up, and the coal we've got now is a little bit dirtier, a little bit messier, and it leaves a lot of ash. You see, if the chemical process goes on and it goes to petroleum, there's much less ash with that. The ash leads to pollution. Okay. Now, coal also contains more sulfur. And when sulfur burns, it goes into sulfur dioxide, just like carbon burning goes into carbon dioxide. Well, does anyone know what carbon dioxide, when it mixes with water, like in the air, it becomes carbonic acid, which is a mild acid. But when sulfur dioxide mixes with water, like in the air, what does it form? Anyone want to make a guess? Sulfuric acid, which is a very strong acid, a very strong acid. In fact, isn't that what you find in most of your lead acid batteries? Sulfuric acid. That you don't want to get on your clothes or on your skin, because you'll have holy clothes and burned skin. Any of you ever experienced that? Battery acid? Yeah. It can do a lot of damage.
Oh yeah, it's no fun.
Yeah.
Got it in my eye once. It wasn't very fun.
What's that?
I got it in my eye once.
Oh no. That was pretty miserable, I bet.
Oh yeah, it sucked.
Okay. Yeah. And sulfuric acid is not a good thing to mess around with. Well, that's what burning a high sulfur coal puts into the atmosphere. Now, I don't know, one of my previous cars was a Toyota, and I bought it at Jim Limbaugh right up the interstate there. And the old guy that used to be the courtesy driver for them, when I would take my car by the shop, and then he'd give me a ride on to campus if I was going to work, he loved to talk, and he was fun to talk with. And he talked about back in the old days in Birmingham when they would blow the boilers. Now, this was either at U.S. Steel or I don't know where it was. Probably everybody was on the same schedule. He said all the housewives knew to not leave their clothes out on the line. This was back before they had clothes dryers, to get them in off the line before the day, whatever day it was, they blew the boilers. Otherwise, they're going to have perforated clothes, because there was so much acid and other really mad stuff in what came out of the air, and that all fell to ground. That was pretty rugged. So all the petroleum, the natural gas, and coal are called fossil fuels. And they're the things that contribute big time to global warming, because they produce so much carbon dioxide and other things. And a lot of that natural gas escapes, and that's methane, which is another really bad pollutant. Okay. Now, another thing we use, and boy, Alabama is probably one of the most blessed states in the nation with the use of moving water. It's renewable because it renews with rainfall. How do we use moving water? Anybody? Look at the third bullet here. Anyone still there?
I know we use it to transport goods.
Right. Okay. Yeah, we use water to transport goods, like the Tom Bigby Waterway and things like that. But I'm talking about using water to produce energy. Yes. Look at a map of Alabama, especially northern Alabama, and you're going to see lakes all over the place. Gunnersville, Smith Lake, Lake Martin, Logan Martin. I know I'm just naming a few of them that I've happened to have driven over. There's lakes all over the place up here. Most of those lakes are not naturally occurring. Someone built a dam there. Probably Alabama Power or Southern Company or somebody built the dam. Maybe TVA built the dam. Dammed up those rivers and streams or creeks or whatever they were, and water piled up on one side. Remember that picture at the very beginning of the chapter? Increased the gravitational potential of that water as it piled up on one side of the dam. Then they let it through, and it falls through the dam, and as it falls, it gains kinetic energy. Same thing we were talking about before, potential energy to kinetic energy, just like your pendulum and those kinds of things. And as it hits the bottom, it hits water turbines, like the steam turbine we saw earlier. Water turbines, those turn with the falling water, taking the energy of that falling water, turning the turbines and producing electrical power. Now, if you go back to the picture here, hydroelectric power was about 3.5%. I don't think that has grown any. Anyone know why? Okay. What I was just saying, bullet number 2 here, gravitational potential energy of the water at the top of the dam converted to kinetic energy as the water falls through the dam. That turns the turbines, making electrical energy. There's the energy conversion process. Okay. Oh, and here it is, about 3% of the U.S. total energy production. It hasn't changed. The growth potential is limited by decreasing availability of new sites. Because guess what? Back when they were building these dams, Alabama, up especially in northern Alabama, was fairly sparsely populated. And the people who lived there were probably fairly poor. They probably were having trouble struggling along as farming, and someone came and offered to buy their property for probably a pretty good rate, and they jumped at the chance. The reason is they were going to build the dam, and that was going to flood that property. And it was, like I said, this was up above what they call the fall line, where if you've driven up, say, in Winston County and places like that, you know how the hills go up and down. That's hard to farm. It's hard to do very much with except maybe grow trees. And even then, it's hard to harvesting those, but they do it. But anyway, those are the kind of places they built the dams. And they flooded those kind of places. Well, now we have much wider and denser populations. To buy up property like that is almost prohibitive. Most of the good sites where it's a good place to put in a dam, there's already dams there. You don't build them down south. If you were to dam up a river down south, you're going to flood 3 counties because the ground is so level, okay? If you build up the dam, it's going to flood huge places where many people live. You couldn't afford that. So the growth potential is limited by decreasing availability of new sites. Back when they built them, I bet you that percentage was close to, I don't know, closer to half of U.S. I doubt if it was quite half, but way more than 3%. But you see, we've gotten more energy hungry, and the number of hydroelectric dams are either decreasing or stayed the same, so our percentage has gone down, down, down. Nuclear. Now, we've already talked about the problems here based on nuclear fission, which is the splitting apart of large molecules, or atoms actually, large nuclei. Usually uranium, which is like 92, I believe, is its atomic number. Plutonium is either 93 or 94, something pretty close. Uranium, plutonium, they're big atoms. And when you hit those with too many neutrons, then they become unstable and they split. And when they do, they give off incredible amounts of energy. But they give off incredible amounts of radiation too. And there's no atmosphere to block it because that's in our atmosphere. Now, yes?
345.
It is 345? How could it be? Okay, let me finish this slide and we'll be through with this then. What we do with that heat is use it to heat water in the reactor, and then we use that to produce steam. That steam then turns the generating turbines, and there you get electricity. Now, it's fairly clean electricity, not releasing stuff into the atmosphere, but you are still generating an awful lot of radioactive material. All the waste product, and there's not a lot of it, but there is waste product there, is all radioactive. And that radioactive waste product, that has half-lives of thousands of years. So that means you have to store it in very carefully constructed containers, sealed very, very well, and buried somewhere for a long, long, long period of time for that to lose its radioactivity. Well, guess what? No one's ever tested these materials to see if they will even hold the stuff for that many years. And then they're buried in a mountain somewhere, and I don't know who's checking that. I sure wouldn't want that as a job, but someone needs to keep a tab on it. And if you start getting radiation there, what are you going to do? Who knows? So the safety, especially of the waste product from nuclear reaction, that's really tough. All right, we're going to start next time with energy sources tomorrow. And by the way, I didn't keep up with it. There is a blurb at the top of page 77, grow your own fuel. Now that's fuel they're talking about, nothing else. A nice little blurb to read. I would suggest doing so. There's a blurb on page 78 on James Prescott Joule. Guess what? He's the one they named the Joule after. A really nice little blurb on him. This cannot be your source for the paper. This may be the source for your idea for your paper, but you can't use this as your source for your idea. You'll see in here mention several other people. English chemist John Dalton, you could write on him if you didn't want to do James Prescott Joule. Later you will see, well, I thought you would see, yeah, there he is, William Thompson. They don't mention his name, but his title was Lord Kelvin. He's the one that brought basically Joule into the fold of scientific activity in England. I'm trying to find where energy sources of tomorrow are. Oh, here they are. Okay. There is a little blurb on city power. That's worth a read maybe. And then there's one at the bottom of page 79. Myths, mistakes, and misunderstanding, recycle or reuse. How does that get into the play? That's under conserving energy, and I don't think we've done enough of that, but maybe we'll hit it when we talk about energy sources tomorrow. But we'll pick up with that next week on Tuesday. And I'm almost certain that we will finish this chapter because we only have a couple pages left to go on Tuesday. So that means on Tuesday we'll probably have a lab, and I'll probably also send you a test. And then after we finish the chapter, we'll do the lab, and you can also do the test. All right, let me end it there. And now I don't want to forget this today, so let me do it now. Has Drew ever come in? By the way, last Tuesday was what, the 31st? And today's the 2nd. I didn't keep my thing up to date. So Drew hasn't made it in, right? Capri hasn't made it in either day. Lydia did turn in some work, so I'll count her present for one part of that. Brianna, is Brianna still here? Yes or no? No? How about Jacob Dove? Is Jacob Dove still here?
I'm still here.
Say again?
I'm still here.
Yeah, okay, so I got Jacob. Okay, he's such a loudmouth, you know, he talks all the time. Kaya, are you still here? Yay or nay? Kaya. Is her name still up? Kaya Dudley.
No, it's not.
She's gone. Sam, you still here? Is Sam still here?
No, it's not.
No, he's not. Tarsha. Yeah, I know Tarsha's here. I see her name up. Okay. Gunnar, you still here?
I am.
Good deal. Is Eric still here? Eric, is his name still up? Eric
No.
Hill. No?
No.
Okay. Zach never made it in today, did he?
No.
Okay. Jeff, I still here, Jeffrey? Jeff? Yep. Kurt, I see. Edward, still here?
Yes, sir.
Okay, I figured you would be. Emily or Katie, we haven't seen yet. Mrs. Lewis, we still haven't seen her since the break, have we?
No.
Mrs. Lewis, is she
She's
here?
not here.
Okay. All right. Jason, you still here?
Yeah.
All right, good deal. How about Ian? I heard him recently.
Yes, sir.
Yeah, I thought so. Josh, are you still here? Josh? Is his name still up? Josh Mathewson?
No.
No. Zane,
Right.
still there? Did I hear
Yes,
him?
sir, I'm right.
I can't hear. Yeah, I see you. I see you. Okay. David Nash, did he ever make it in? Don't think so. Okay. Wait just a minute. I've gotten behind. All right. Oh, I've skipped Anaya Nunn. She hasn't made it in, has she?
No.
Okay. Jacob Porte, still here?
Yes.
Yes, good. Jose, still here?
I'm here.
Oh, good. Tiffany, still here? Did we lose Tiffany Silcox? Is she?
She's not here.
She's not there. Okay. Perrin, I saw you recently. You still here?
Yes, sir.
Okay, good deal. Cash, you still here? Yeah, no.
Cash is here.
Cash is here. Good. And Chad, you still with us?
Yes.
Okay, good. All right. And in case, since we have lost someone, I'm sorry I didn't say it a little sooner. Don't ever think we're not having class unless you've heard we're not having class. So if you don't hear anything from me, keep looking somewhere, because call some of your friends something, because I'm not going anywhere. You know, I don't leave, and I'm going to be here. We're going to have class every day, every Tuesday and Thursday. So don't assume we're not having class. All right.
Dr. Brown.
Yes.
Hey, thank you. I'm sorry. I still had my computer on mute because I didn't want you to hear my background. Natasha told you that I was still here. Thank you.
Okay. Who is this?
This Cash, you had asked was I
Oh,
still
yeah.
I kept saying here, but my computer was on mute because I didn't want you to hear my background.
Right. I understand that. That's you can mute so it doesn't bother everybody else, but I hope you don't mute it so you can't hear us.
Oh, no, I can still
Okay.
hear you when I mute, but you can hear my noisy background.
Right. I understand. We had
Yeah,
that.
I still hear you.
We had that this morning with someone who wasn't muting, and it was pretty bad. He apologized. Okay, but thank you for doing that. Okay, so let's go on and get out of the slideshow here. you're going to lose the screen for a minute, but I hope you won't lose connection because I'm going to close this out. Well, let's see. Oh, I see Eric. Did I get Eric before? Yeah. Eric's back. Okay. I think that's you, isn't it?
Yes.
All right. It's still not helping a lot. I'm having to move things around so I can. Need to close out. There we go. All right. Screen sharing is stopped. Ah, there's my list. Okay. All right. I guess I've got everybody. I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Well, maybe that's all. Okay. I know that screen sharing has stopped, but oh no, there's 2 more. I may not have everybody. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I'm missing 2 people. Tiffany is not listed there, is she?
No, but
Josh,
is.
I think Josh is one of them. Who did you say?
Joshua Matheson.
Yeah, I think I saw his name, didn't I?
Yes.
Okay, I don't see it now. There it is. Yeah, right at the bottom. He came back. Welcome back. That's 1 more. Sam, is Sam back? I don't see Sam. Kaya. Oh, was that Sam saying something?
No.
No, okay. Is Kaya back?
No.
No. But Bree, I think I missed Bree. I see you
Yes,
there.
I'm back.
Okay, good. All right. So let me go to, this is going, I need to minimize. Oh, there it is. Exit full screen. Right there in front of me. Okay, I got to minimize that for a moment. And I think this is the screen I want. So I'm going to minimize this for a moment. Nope, I went the wrong way. That way. Okay. Nope, that's not the screen I want. Get rid of that one. And here's the one I want. Well, sorry it's taking so long. Okay. Most of you have your, whatchamacallit, your labs, don't you?
Yes, sir.
Okay.
Yes.
So I was going to open this, but that's going to be too many things open. So what I'm going to do is go to, okay, I'll be back in a minute. Yes. Hello. Yes. Did you need something?
Kaya is back.
Oh, Kaya is back. That's what she needed. Okay. All right. Someone ran to get her, didn't they? Okay. All right.
We got the phone. I'm back.
Okay, got it. Thank you.
All right, thanks.
I'm trying to get, I should have had this open already. I don't know. Can y'all see me doing this, or you just see a blank screen?
I just see the top of your hand looking at your computer.
Okay. That's my best part, by the way. Okay. Oh my goodness. I'm stiff from sitting here too long. That's why I like being in the classroom. I get up and move around. Y'all have to sit, but I get to move. And now I'm stuck at a chair. Okay. Well, password's not passing. Okay, here we go. Okay, I'm going to try to get us back. Okay, and return to meeting, and go and share a screen. I think that's the one I want. Okay, can y'all see that now?
Yes, sir.
Okay, that's part of my Blackboard. I don't know if you have a page that looks like this, but anyway, I'm going to our course, which is down here. There we are. Now this is how you get to your labs. Did everybody see it so far? Go to get to this course in Blackboard. Now, go to the, okay. Now, while we're here, do you see that bar I'm talking about? There's the message icon. I'm going to move this thing. This is just in the way. Okay. All right. I don't know what this thing, oh, that's the content. That's where we are now. Here is the calendar. I'm not using that much. Here is our discussion group, which I'm not using. Here's the grade book. Is that where y'all see your grades? Or you see it some other way? Say again?
Yes, we see the grades.
Is that how you see it, through this grade book or something else?
I see it through that.
You do, okay. Here are the messages, okay? And then this one over here is analytics. I don't know what that is. I don't use it. Okay, so that's what that looks like. Now I've got to get this thing out of the way again. I'm going to move it over here this time. Okay, so I can scroll down here to see, whoa, I do not like this new Blackboard at all. Okay. I've got, this is so aggravating right here. Okay. If you get anywhere close to that question mark, I get it up. Even if I'm not even on the question mark. I'm on the arrow, but if I'm too close to the question mark on the arrow, it doesn't do it. It drives me nuts. Okay, there's the announcements. Is that where y'all see your announcements too? Okay. All right. Then you get down to course content. That's what I was looking for. And here you get to laboratory simulations. And by the way, there's the library link. I think I was talking about that earlier. Everything's going virtual. The library link is right there. Okay? But here, and by the way, right up here is the YouTube videos. So if you missed a class, that's where you go for YouTube videos. Missed the lab, that's where you go for YouTube videos. They're usually embedded in the class. There's one of them that's not. So they're all out there. Here's the laboratory simulation. So go to that. It sometimes takes a while to open. And then you go to simulations here. If you got your lab, you see that I'm walking you through this now. Go to Blackboard page for the course. Go to course content. Scroll down to laboratory simulations. Click on simulations, then on physics. That's what I'm going to do right now. Click on that, and you're going to get a whole big list of them. They're mostly alphabetical. So scroll down. Today we're looking for Energy Skate Park. So we got to go through our B's, through our C's, through our D's, and now we're into Energy Skate Park. Not the basic one here, the Energy Skate Park here. I can't say it very fast. So click on that one. Okay. Now, I used to say do download. I think this arrow does it too. So I'm going to try the big arrow now and see if it opens it. This one I think takes a little while to open. And this one says this type of file can harm your computer. Do you want to keep it? I say keep because that's the better one that I found out of these. So there's the keep. Hopefully it won't harm my computer. Okay, but it still has it open, so I'm going to come over here and click on this and see if it opens there. If it doesn't, go to the arrow and open when done. I don't know what it's doing, but open when done. And again, it takes a while. Be patient. I think it will come up. There it comes. It's starting up now. There we have it. Okay, I don't think I need to see this. Okay. Yes.
Someone is calling you.
Someone is calling me.
Yeah, Jason.
Okay, who's calling?
Jason.
Jason.
Whenever I tried to do the moving man and the ladybug one,
Right.
it would not let me do that. It would go to the part where it says keep or discard, and I would hit keep, and then I'd hit open when done, and then it just wouldn't do anything. That's exactly what mine does too.
And who is that?
Jeffrey.
Jeffrey. Okay. Yeah, you said that last time, didn't you?
Yes, sir.
Okay.
Whenever you scroll through the list, as long as it says the HTML5 or whatever that says, as long as it says that, then I can do it because it has played in a thing. But as soon as it tries to download, it gives a never-ending loop. You can't get into it. I can't get into it. Yeah,
Okay.
I can't either. Mine does Java, and I have Java downloaded. I do too.
Okay, the most current version. Is it?
Yes, sir.
Okay. That was your problem, wasn't it, Tasha?
It was, but I fixed mine. Sometimes I have to click on the picture to download it, or I'll click on download. So either way can work.
Yeah, I tried both of them.
You did try both.
And
Okay.
then I'd go to my download folder and try to open it from there after it got done downloading. It's the same thing. Yeah, then it would just pull up three options: open, save, or save as. And no matter what you click, it still does absolutely nothing.
Okay. Now, what I would suggest is, let me go on and give you their email addresses. I'll try to remember to email them myself, but tell them you're in my class and other students have had the problem. Because, Tarsha, did you go to Miss Glass or Mr. Mankiewicz?
Yes, I went to him.
Him. And it took him a while, but he figured it out. Both of those people are incredibly good at what they do. And especially Miss Glass is just one of the nicest people you ever meet. She doesn't speak computerese. She's very, very easy to work with. And Mr. Mankiewicz is too. He's just a little more high-strung maybe, but he's still a really nice guy. So go to, it's jglass@lawsonstate.edu. That's J, the letter, Glass, glass like broken glass, at lawsonstate.edu. And Mr. Mankiewicz is JMankowich, I think. That's a hard word to spell, and right off the top of my head, I think that's what it is. J. Mankiewicz, Mankowich. And he is usually pretty busy, but he found time, and he was helpful for you, Tarsha, right?
Yes.
Okay. So he can be ready to give him all the information you can. You know, what kind of system you have. What all did he ask you, Tarsha?
Well, I just told him that I was having problems opening the file, and Miss Glass transferred me to him, and he sent me to www.java.com.
Okay.
He told me that if I had any issues connecting it, he would call home.
Okay. So he'll follow up if he can. what you can do, folks, if you can watch it on the, I demonstrated it a few times on that YouTube video. Try to stop and capture and just base it on what I did, because I think I went through the whole exercise. It's not very much to do, but write down what you can, what you see, what you notice. For the moving man, basically it was the relationship between his speed and his position, what those were doing. And you'll see those on the thing. Listen to what I say. Try to answer the questions based on what you can see there. And it's only a couple of questions. These are really short laps. The ones we're doing now, they're more substantive. But I just didn't have time to put those together. I didn't have time to type them up. These, I barely had time last night to do this, but those first two, just get me something, and you'll get credit.
Okay, I didn't have, our printer isn't working right now, so I couldn't print off the lab for today. Do I just need to write it down?
Okay. Can you, let's see, you probably can't pull it up on your screen and look at it while we're talking, can you?
Like, just to type into the Word document?
It's in a Word document, yeah.
I typed in the one for the lab on Tuesday and emailed it to you. I don't know if you received it.
Who is this talking?
Jeffrey.
Jeffrey, yeah, I think I did get it, but you may not have been aboard when I was saying this week I have been in meetings just about as much as I've been in class, and I have 8 different subjects I teach, and so I'm in class most of the time, and every moment I haven't been in class just about, I've been in a meeting. So I'm behind in my grading, and even behind in printing them off. I can't remember if I printed yours off or not, but I do think I remember seeing it. I'm hoping this evening, after I finish going through the summer schedule, hopefully that won't take too long, I'll be able to print off some of the things, and then tomorrow morning, the trouble is, my wife's at home working too. She's got the office downstairs. That's where the printer is. I'm in a bedroom upstairs, so when I talk, I don't bother her. So that's unfortunately how we're having to do things here. So I can't print in the day while she's down there, but most of the time I'm in classes anyway. But tomorrow morning I have free time. But if she's not using the printer, then I'll be able to take the printer and print it from up here or somewhere else. But if she is using it, then I'll have to wait till she's through to print off the rest of them. So I'm going to try to get caught up this weekend, but I'm way, way, way behind in printing them off, and then way even further behind in grading. So I'll try my best to get that done. Okay. Yeah. All right. So what we've done, we've clicked on download. Is everybody be able to get on this one?
Well, your screen is blank.
Say again?
The screen is blank.
I still can't hear you. Oh,
The screen is blank. We can't see anything.
oh, you can't.
No.
It says my screen sharing is paused. Oh, why is it paused? I thought I did that. Oh, wait. Oh, I see. It stopped when I left Blackboard. Okay. Thanks for telling me. Let's see. Can you see this now?
Yes.
Okay. Did you see this before? No, you didn't.
What was that whenever you were first showing us that to do this button?
Okay. So I guess I'll go through this again. Let's see if it's still here. No, it isn't. Okay. So here's the keep. Y'all didn't see me do this? Oh, okay. I lost you then. You should have stopped me then. Okay, let's see if I can get it started from here. Open when done. Okay, I'm guessing you probably won't be able to read the thing at the same time you're watching this. Yeah, I don't see how you could do that. It's slow opening. Let me try it again. Open. Open Sesame. There it comes. Okay, I thought you... Ah, there we are. We're back. Okay. Are y'all seeing it now? No, it still says the screen sharing is paused. Let me try a new share again. Can you see it now?
Yes.
Ah, good. Okay. There's too many moving parts here besides the guy on the skateboard. Okay. So we've done everything we have. We click on download, it did. We click, it opened. Adjust the sim speed. Now that's down here. I just say to do this so you can do things a little more easily. So I usually slow it to about midway. Okay, then it's a little easier to keep up with. Okay? If you want to keep it fast, you can. I don't care. Okay? Then choose a skater. So come up here to the top, and it says choose a skater. You see where I am? Upper right? See my cursor?
Yes.
Okay, choose a skater. Now you can choose any one you want. You got 5 to choose from. You got they call him the FET skater, that's the physics something another. Here's the star skater, the bulldog, the bug, and the ball. The ball should be between the bug and the bulldog. Okay? When you choose it, you also record the skater's mass. So I'm going to go with this guy. And the trouble is, the print is in the way. There we go. Fat skater, 75 kilograms. Now, you don't have to choose him. That's just the one I'm going to choose. So that's what I would put in there, 75 kilograms. Okay? But when you choose him, put it in because you're not going to see it again. Okay? So I'm going to choose him. And now I've got to go back and hit OK. Trying to get to OK. Let's see if I can get to it now. Yuck! I don't know why it's doing this. Okay. I think this is the one we were in. Boy, it's not this hard when you don't have all these things on the screen. For instance, can you see this thing that's called ID blah blah blah? Okay. Can you see what I'm doing now?
Yes.
I'm back with the energy skate part, but it's not the guy skating.
Correct.
Okay. Oh, wait. Need to keep this. Okay. I'm going to discard that one. Okay. Open when done. I guess it takes a long time before it gets done. All right. Hopefully it's going to start soon. There it is. Okay, can you see the skate park now? The guy going back and forth. Okay. So I've got to come back here and do a new share again. Okay. Keeps taking me back to here. I'm going to quit going there. New share. Let's try this one. Can you see that? The guy going back and forth.
Yes.
Okay. All right, we chose the skater, and whichever one you choose, when you choose them, pick the get the mass at the same time, because you don't see it anymore. Okay, I suggest getting the measuring tape, and you see the FET measuring tape there. Okay, we're going to use it later. It says potential energy reference. Click on that, and I put it down here at ground level. If you're all right with it there, leave it there. If you want to move it, you just click on it and, well, I thought you just clicked. There. Click it and go up or down with it, wherever you want it to go. I would suggest don't bring it above the lowest point. You can either leave it where it is or bring it, but don't take it any higher than this lowest point here. Okay? I also like to use the grid, so I'm going to put the grid in. And then show path. We'll probably do that later, but not right now. But I'll show you what it does. You see it. It's like a stopwatch, and every time he gets a second or something passes, it puts another button. But you see, it just sort of messes up things. So I'm going to stop it and clear it. Okay. We might go back to that later. On show pie chart, it really doesn't show much except kinetic energy is green, potential energy is blue. We're not doing thermal energy, so forget about that. And you don't see any of there either. Oh, here's what the pie chart does. It's showing the portion of it that's green, blue, and that's your portion. One reason it doesn't go to 0 at the bottom is your reference level is here, your lowest point is there, you still have some potential energy. If he fell off, he would go down to the ground level. Okay. Now, we'll do the bar graph later, but you see it takes up, well, it takes up part of the screen here, but we'll come back and do that. So I'm going to clear this out of the way. I don't think we need energy versus position or energy versus time. Let's stay on the Earth for now. If you want to change it later, you can. Now, I wasn't paying attention. It said click on the measuring tape and click on potential energy reference. Place the potential energy reference somewhere on or between the ground and the lowest point. I told you that. With the measuring tape, measure the distance between the potential energy reference and the lowest point on the track. So what you do, you grab the measuring tape here, take it down here to the lowest point, right there, or thereabouts, and then take the end of the tape and twist it over here to the ground level. Okay? Try to get it as level as possible, as vertical as possible. And what's your height? Record that, 1.5 meters. Now, if you move the potential energy level, you'll have a different reading there. Okay? So that's the distance, lowest point on the track, 1.5 meters for the one I'm doing with that guy on it. Okay? Now, I've already clicked on the grid and showed the pie chart. If it's not already there, check on location Earth. Yeah, it was already there. Okay? At that point, record the acceleration due to gravity there. Now, they use some weird units, newtons per kilogram, but that's indeed the same as meters per second squared. So there's an acceleration due to gravity on Earth, and if you, I would use the units meters per second squared, but if you want to use newton per kilogram, it's the same measure. Now, I'll just show you what happens. If you go to space, he doesn't ever come back. Okay? So what you have to do is return the skater. Okay? Come on back, skater. Okay. No gravity there. The moon is 1.62 newtons per kilogram or meters per second squared. Jupiter, 25.95 meters per second squared. Okay. But I like to stay on Earth. Besides, Jupiter is all gas, he would collapse. So anyway, let's go. Well, he's in the air anyway. So I think we've got all the settings done. You can play around with other things if you want to, but just record what you're doing. Okay, with the measuring tape, so you recorded the gravity. With the measuring tape, measure the distance between the potential energy reference and the highest point the skater reaches on the track. Okay, so what we're going to do, I'm going to move this up to go as high as he goes. I'm going to have to, he has a little red dot on his skateboard, and that's what I want to get if I can catch him there. Whoops, a little bit further. Maybe a little further. I think that's about it. See, the grid line helps because he's going just about there. So that's going to be one place. And then I'll go down to the zero reference level, or the potential energy ground level, whatever they call it. That's where your potential energy is 0. Okay? And for me, that's about 5.03 meters. I think I made my, whoops, on the wrong thing. I can't get my thing back. I hate to move this, but I'm going to. Okay. This is very slow. Now, see, he's going just below that line. Okay. So I'm going back down here. Nope. Why does it keep picking up? There we go. Okay, now it's about 4.95. That might be closer. I don't know. Whatever you do it. Okay? But that's how you use the tape measure. Well, when you get close to that line, it's hard to separate them. That's going to be close enough. Okay, you recorded that. Okay. Now, that's your measurements. Now you start your calculation. First, calculate the potential energy at the skater's maximum height. Well, you know the formula? Potential energy? Anybody? Anybody? Potential energy formula. Nobody knows it. Is it? Say again? MGH. Excellent. Okay. You know his mass, or whoever mass you chose. You know the G, that's right over here, and you know the height. You just measured it there. And all those units are correct. The gravity is in 9.8 meters per second squared, so that's what I would use. Now determine the speed at the maximum height. When he gets right up here, how fast is he going? At that moment, when he reaches that point, what's his speed? 0, because he stops there and then starts going back the other. So at the moment he reaches that highest speed, his speed is 0. So what is kinetic energy at the highest point? What's the formula for kinetic energy? Anybody remember? 1/2 mv squared, exactly. Well, his velocity is 0. What's his kinetic energy? 0. Very good. So what would be his mechanical energy at that height? What is mechanical energy? Anybody remember? Does anyone remember? I said we'd be using it today. Yeah, it's the sum of the potential and kinetic. Potential was up there. I didn't put a number by it, but it was a couple lines up, 4 lines up, and kinetic was just above this. You add those two together, There's the mechanical energy. By the way, what units are energy measured in? Anybody? Ladies, tell them. Joules, exactly. Okay. Now, what we're going to do now is calculate the potential energy at the skater's minimum height. You already know the formula there, right? mgh. You recorded the mass up in the first thing when you chose the skater. Then you determined you had the distance there right below that, and you know what g is. So in this case, if you have your potential energy line down there, he still has potential energy because he could fall off and hurt himself, okay? It's not at ground level, so he still has some potential energy, okay? So what's the mechanical energy at the minimum height? Now you probably can't give me a number, but tell me what it would be. Anyone have an idea? Don't give me a number, just tell me what it would be. Let me give you a hint. Mechanical energy is conserved. So the mechanical energy at the top is the same as the mechanical energy at the bottom. Right? Yes or no?
Yes.
Yes. Okay. So, if you know the potential energy at the bottom and you know mechanical energy at the bottom, you can calculate the kinetic energy at the bottom. How? What is mechanical energy? You answered right before. Say again? Yes, kinetic plus potential. So if you know mechanical energy, subtract potential from it, that gives you kinetic energy. Right? Now, we didn't do this one in class. We did something similar to it, but don't use the formula we did in class. The speed of the skater at the minimum height, because you're not at the zero reference level, you can't use that formula. V final is equal to the square root of 2gh. You can't do that because you're not at the bottom. The potential energy, it still has potential energy here. So here's what you do. I'm going to see if it'll write on here. I don't think it will. Yuck. Yuck. I thought my pen would write on it, but it won't do it. Okay? If you write this down, kinetic energy equals 1/2 mv squared. Write that down. Ke equals 1/2 mv squared. Okay? On the line just above that, you recorded the kinetic energy at the bottom, right? Okay? And you know what 1/2 is. Multiply both sides by 2 and you get twice the kinetic energy is equal to mv squared, right? Just multiply both sides of that equation by 2. Okay? So you got mv squared equals 2ke. So you can figure out the ke later. Okay? Now, divide both sides by m. That mass that you have up at the top. Record the skater's mass. Okay? And then you have v squared is equal to 2ke divided by m. Right? Take the square root of that. And you have v is equal to the square root of 2ke divided by m. Okay, when you get your numbers filled out, that's how you determine the skater's speed. Okay? The speed at the minimum height. Okay, when you've done that, go up here and choose a different skater. I don't care which one you did first. I don't care which one you do second. Just make sure it's a different skater. Okay? If you chose the guy at the top, you can use the star skater next, or the bulldog, or the bug, or the ball. I don't care. Okay? But whatever one you choose, different from before, record that skater's mass. Then you go through the whole process again. Calculate the potential energy using that skater's mass. Okay? You do it at the maximum height. That hasn't changed. You do it the speed at the maximum height. That didn't change. You do the kinetic energy at the maximum height. That didn't change. And you do mechanical energy. That will change because you have a different potential energy. Okay? Then calculate potential energy at the minimum height. Because you have a new mass, that will change. Mechanical energy at the minimum height, because you have a new height, that has changed too. And then the kinetic energy at the minimum height, that will change because you have to subtract from those two others. Okay? And then you calculate the speed just like you did before. So you go through that whole exercise again, and as soon as you get that one finished, go back to the top and choose another skater. Choose one different from the other two. Okay? And when you get that one chosen, record his mass before you leave the screen. Okay? And then you go through the same exercise again. Is there any question on this?
No, sir.
Okay, does it sound like it's reasonable?
Yes, sir.
Okay, now here's the part I forgot to do. Like I said, it was after 10 o'clock last night before I finished this and was ready to send, and I completely forgot the most important questions on here. Okay, and here's what they were. So you can write these on the back on another piece of paper or whatever, but when you send me, you can write it at the top margin, the bottom margin, wherever you want to. Which energy is conserved? It's a multiple choice, either potential, kinetic, or mechanical. I've already said it a couple times. Hopefully you know that one. That's an easy one. Okay. Looking at the three skaters, now that is for any one skater, which energy is conserved. Okay, I should have said that. For any one skater, which energy is conserved? Potential, kinetic, or mechanical. Okay, and when you look at your answers there at the top and the bottom, you'll see which ones doesn't change. But when you look at the different skaters, what do you notice that doesn't change about them between the three skaters? All your energies are going to change, but one thing won't change. And I wonder if you'll pick up on what that is. So that's the second question. The first one, looking at any one skater, which energy doesn't change? Which one is conserved? And the answer would be either potential, kinetic, or mechanical. You look at the data, answer that question. But then look at the three different skaters that you chose and see what quantity never changed. Okay? One of your calculated quantities. Not the distance, not the thing that you measured, the calculated quantity. And you calculated, if you look at the questions, you calculated potential energy, mechanical energy, top and bottom. You calculated kinetic energy at the minimum, and you calculated speed at the minimum. Look at all those calculations, what never changed between the three different skaters. Or it didn't change much, I'll put it that way too. Okay, so those are the two extra questions. For any one skater, which energy was conserved? In other words, which energy never changed within a skater? And then among all three skaters, which calculated quantity had the minimum amount of change? You may be a little surprised at that. You may not, depending on how closely you were listening to things in class. Okay? I think there's room to write both of those in any one of the margins. Actually, the bottom margin of the first page or the top margin of the second page look like they got put in, or you can put one in one place and one in the other. Wherever you want to put them, answer those two questions. All right. Are there any questions on this lab?
No, sir.
Okay. Now my question to you is, do you want me to leave this up while y'all are doing it so you can try to call me or contact me on this and I'll still be here? Or do you want to just work on it? And then if you have questions, email me or whatever. You need this left up. If you want to go take a break and want to work on this later, you certainly can do that. What do y'all want to do?
I think we should just call it here.
What's that?
I think we should call it here.
Call it here. You mean work on it here?
Or just end it here.
I didn't understand what you meant. It may be...
I think we should end it here.
End it here. Oh, I see. Okay. Well then, if that's what you're recommending, I'm going to shut down. Oh. Before we do that, I said we would do this, and I do want to do it. And this feeds into one of the things I was talking about. Here's that bar graph again. Okay? And this is almost giving it away. This is following the skater here. The kinetic energy and potential energy. The total energy, that column, you could call that, what would you call that one? The title, one of the names that are on the lab sheet. Not total energy, but what was the other name for it? What's the only? Mechanical. That gold bar is the mechanical energy. And that answers one of those questions I think I just did. And you can do this for the whichever of the skaters you do. Now one thing I wanted you to notice, when he gets to the bottom down here, notice that he's got his maximum kinetic energy, but he maintains some potential energy because he still is a height above the potential energy line. So that's why I wanted to show you this. That helps you answer that other question. In fact, that helps you answer one of those questions, I think, pretty well. Okay? All right. Any questions yet? So I'm going to shut down the bar graph. I will shut down the skater. It just did. Okay, we've lost the screen sharing. Now, has anyone else added the class since I called roll for lab? I think I've got all of these names, don't I? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, we've lost some even since then. Okay. So I'm going to go on and end that. End the meeting for all. Oh, there's where I needed to. End the meeting here. End the meeting for all. We'll see you next Tuesday.